A very brief history of time. I just had a chance encounter with a garden slug, and it got me thinking about time. In this ostensibly inanimate, impersonal universe, a garden is a miracle. All the more so is a garden slug, an animal that can extract sufficient energy from the garden's vegetable matter to move from place to place under its own power. When one is in the right mood, watching the shimmering spotted slug slide over the mulch evokes the miracle of biology in all its splendor. The creature's pulsating aliveness is hypnotic. But then one recovers his bearings and realizes that this is only, after all, a garden slug, and that the ladder of biology goes much higher. The miracle of life has culminated in one's own species, man. Unlike the slug, whose nervous system has barely enough complexity to let it interface with the environment, a man's nervous system, nucleated by the adaptive and inventive human brain, can abstractly model its surroundings and project itself consciously and creatively through time. A slug can learn. The small neural network that serves as its brain can be modified by sensory input from its environment, and the slug's behavior modified accordingly. To this extent, the slug remembers the input. But because its simple brain cannot form an internal model of its changing relationship with the garden, the slug cannot recognize its memories as changes. The state of its nervous system at any given moment can pass for all that it has ever known. Because the neural function by which the slug identifies self is instinctual and perceptual as opposed to cognitive, because the slug defines itself strictly by non-reflective instinctual processing of environmental stimuli, the dependent neural function time is limited to here and now. The slug recognizes no past self or future self on which to define an extended temporal relationship. As the slug's primitive example shows, our awareness of time depends on the extent to which our mental models of reality reflect change. To see an object change, one must recall its former state for comparison to its present state, and to do that, one must recall one's former perception of it. Because perception is an interaction between self and environment, this amounts to bringing one's former self into conjunction with one's present self. That past and present selves can be brought into conjunction across a temporal interval implies that momentary selves remain sufficiently alike to be conjoined, that they can intersect at any given moment. To compare content means that the intersection is changeless. So when self is generalized as the intersection of all momentary selves, it acquires a property called time invariance. It is the rock of perception, the unchanging observation post from which the net of temporal connections is cast and to which it remains anchored. Indeed, it is the fabric from which the net is woven, its relationship with the environment serving as the universal template for all temporal relationships. Through learning, mental models of time evolve in time. As the brain's neural connections are modified and the strengths of existing connections are adjusted to account for new information regarding both self and environment as it learns, its model of time changes as a function of time. In other words, the model changes with that which is modeled. If the brain is smart enough, then it can model itself in the process of being changed, and depict its own learning process as a higher level of time. But even as the self absorbs its educational history and deepens its reflexive understanding, it remains static at its core. Otherwise, it would lose temporal cohesion and fall apart. Since self is static, time too should possess a static description that does not change in the temporal flow it describes. If time were the water flowing in a river, then a static description of time would be analogous to the rocky banks that determine the river's course. Such a description arises by abstraction. As cognitive models become more sophisticated, cognition becomes increasingly abstract, concepts become increasingly independent of the particular objects they describe. Among the first things to be abstracted are space and time. The most general abstract system incorporating both is a language. Although the term language usually refers to a natural language like English, it is actually more general. Mathematically, a formal language consists of three ingredients: a set of elements to be combined as strings, for example, symbols, memes, a set of structural rules governing their arrangement in space, and a set of grammatical rules governing their transformations in time. Together, the latter two ingredients form the syntax of the language. It follows that neural, cognitive perceptual, and physical systems can be described as languages, and the laws which govern them as their syntaxes. On a subjective level, time itself can be abstractly characterized as the grammar of the joint language of cognition and perception. The rules of this grammar are the general ingredients of subjective time. Because time is defined in terms of transformations among spatial arrangements of objects, it is conceptually entwined with space. Thus, it is actually part of a linguistic complex called space-time. Spatio-temporal relations exist on many levels. If level 1 consists of simple relationships of objects in space and time, then level 2 consists of relationships of such relationships, and so on. Because logic is stratified in much the same way, one can say that time is stratified in a manner corresponding to predicate logic. This must be true in any case, since any meaningful description of time is logically formulated. Spatio-temporal stratification allows time to be viewed on various scales corresponding to ascending series of contexts, for example, personal awareness, interpersonal relationships, social evolution, evolutionary biology, and so on. The histories of people, institutions, cultures, and species are nested like Chinese boxes, with the abstract principles of each history occupying a level of temporal grammar corresponding to an order of predicate logic. Because of the relation between self-awareness and temporal awareness, temporal stratification induces a stratification of self. What we have already described as the static intersect of momentary selves becomes a stratified relationship, a terrace of temporal vantages conducing to long-term self-integration. As the self becomes stratified, the principles abstracted from higher orders of experience tend to be objectivized due to their generality, with science and philosophy among the results. Thus, the subjective and objective sides of reality, the self and the environment, tend to merge in a symmetric way. On one hand, the environment is absorbed by the self through experience, and the laws of nature are thereby abstracted. On the other hand, the self is projected onto the environment in such a way that it selects the laws of nature by analogy to its own internal laws. Either way, the core self tends to intersect with the environment as momentary selves are intersected within it. This brings the subjective and objective phases of reality and time into closer correspondence, blurring the distinction between them from an analytic standpoint. As time grows more abstract, ways are sought to measure it, diagram it, and analyze it numerically. This requires a universal depiction of space and time against which arbitrary processes can be differentially graphed and metered. Such a depiction was introduced by the Frenchman René Descartes in the first half of the 17th century. It was called analytic geometry, and it depicted time and the dimensions of space as straight, mutually perpendicular axes. In analytic geometry, any set of numerically scaled space and time axes associated with any set of properties or attributes defines a coordinate system for assigning numbers to points, and simple processes appear as the graphs of algebraic functions. A few decades later, Newton and Leibniz independently discovered a new kind of mathematics, the infinitesimal calculus, by which to numerically quantify the rates of such processes. These innovations, which laid the foundations of modern science and engineering, suffice to this day in many practical contexts. Even though garden-variety analytic geometry was technically superseded by the theory of relativity, which was itself constructed on an analytic geometric foundation, it gives a very close approximation of relativity in most situations. Unfortunately, the conveniences of analytic geometry came at the price of mind-body dualism. This was Descartes' idea that the self, or mind, was a non-physical substance that could be left out of physical reasoning with impunity. For some purposes, this was true. But as we saw in the next to last paragraph, the relationship of mind to reality is not that simple. While the temporal grammar of physics determines the neural laws of cognition, cognitive grammar projects itself onto physical reality in such a way as to determine the form that physical grammar must assume. Because the form of physical grammar limits the content of physical grammar, this makes cognition a potential factor in determining the laws of nature. In principle, cognitive and physical grammars may influence each other symmetrically. The symmetric influence of cognitive and physical grammars implies a directional symmetry of time. Although time is usually seen as a one-way street, it need not be. The mere fact that a street is marked one way does not stop it from being easily traveled in the unauthorized direction. Indeed, two-way time shows up in both quantum physics and relativity theory, the primary mainstays of modern physics. Thus, it is not physically warranted to say that cognition cannot influence the laws of physics because the laws of physics precede cognition in time. If we look at the situation from the other direction, we can as easily say that cognition precedes the laws of physics in reverse time and point to the strange bidirectional laws of particle physics to justify our position. These laws are of such a nature that they can as well be called laws of perception as laws of physics. Before we get to the final word on time, there is one more aspect of physical grammar that must be considered. Physical reasoning sometimes requires a distinction between two kinds of time, ordinary time and cosmic time. With respect to observations made at normal velocities, ordinary time behaves in a way described by Newtonian analytic geometry. At higher velocities, and in the presence of strong gravitational fields, it behaves according to Einstein's special and general theories of relativity. But not long after Einstein formulated his general theory, it was discovered that the universe, aka space-time, was expanding. Because cosmic expansion seems to imply that the universe began as a dimensionless point, the universe must have been created, and the creation event must have occurred on a higher level of time, cosmic time. Whereas ordinary time accommodates changes occurring within the space-time manifold, this is obviously not so for the kind of time in which the manifold itself changes. Now for the fly in the cosmological ointment. As we have seen, it is the nature of the cognitive self to formulate models incorporating ever higher levels of change, or time. Obviously, the highest level of change is that characterizing the creation of reality. Prior to the moment of creation, the universe was not there, afterwards, the universe was there. This represents a sizable change indeed. Unfortunately, it also constitutes a sizable paradox. If the creation of reality was a real event, and if this event occurred in cosmic time, then cosmic time itself is real. But then cosmic time is an aspect of reality and can only have been created with reality. This implies that cosmic time, and in fact reality, must have created themselves. The idea that the universe created itself brings a whole new meaning to bidirectional time, and thus to the idea that cognition may play a role in the creation of reality. As a self-creative mechanism for the universe is sought, it becomes apparent that cognition is the only process lending itself to plausible interpretation as a means of temporal feedback from present to past. Were cognition to play such a role, then in a literal sense, its most universal models of temporal reality would become identical to the reality being modeled. Time would become cognition, and space would become a system of geometric relations that evolves by distributed cognitive processing. Here comes the surprise, such a model exists. Appropriately enough, it is called the cognition-theoretic model of the universe, or CTMU for short. A cross between John Archibald Wheeler's participatory universe and the Stephen Hawking James Hartle imaginary time theory of cosmology proposed in Hawking's phenomenal book A Brief History of Time. The CTMU resolves many of the most intractable paradoxes known to physical science while explaining recent data which indicate that the universe is expanding at an accelerating rate. Better yet, it bestows on human consciousness a level of meaning that was previously approached only by religion and mysticism. If it passes the test of time, and there are many good reasons to think that it will, then it will be the greatest step that humanity has yet taken towards a real understanding of its most, or least, timeless mystery. And so the circle closes. Time becomes a cosmogonic loop whereby the universe creates itself. The origin of our time concept, the self, becomes the origin of time itself. Our cognitive models of time become a model of time as cognition. And the languages of cognition and physics become one self-configuring, self-processing language of which time is the unified grammar. Talk about time out of mind. And all this because of a little garden slug. The theory of theories. You know what they say about theories, everybody's got one. In fact, some people have a theory about pretty much everything. That's not one master theory of everything. Mind you, that's a separate theory about every little thing under the sun. To have a master theory, you have to be able to tie all those little theories together. But what is a theory? Is a theory just a story that you can make up about something, being as fanciful as you like? Or does a theory at least have to seem like it might be true? Even more stringently, is a theory something that has to be rendered in terms of logical and mathematical symbols, and described in plain language only after the original chicken scratches have made the rounds in academia? A theory is all of these things. A theory can be good or bad, fanciful or plausible, true or false. The only firm requirements are that it, 1. Have a subject, and, 2. Be stated in a language in terms of which the subject can be coherently described. Where these criteria hold, the theory can always be formalized, or translated into the symbolic language of logic and mathematics. Once formalized, the theory can be subjected to various mathematical tests for truth and internal consistency. But doesn't that essentially make theory synonymous with description? Yes. A theory is just a description of something. If we can use the logical implications of this description to relate the components of that something to other components in revealing ways, then the theory is said to have explanatory power. And if we can use the logical implications of the description to make correct predictions about how that something behaves under various conditions, then the theory is said to have predictive power. From a practical standpoint, in what kinds of theories should we be interested? Most people would agree that in order to be interesting, a theory should be about an important subject, a subject involving something of use or value to us, if even on a purely abstract level. And most would also agree that in order to help us extract or maximize that value, the theory must have explanatory or predictive power. For now, let us call any theory meeting both of these criteria a serious theory. Those interested in serious theories include just about everyone, from engineers and stockbrokers to doctors, automobile mechanics and police detectives. Practically anyone who gives advice, solves problems, or builds things that function needs a serious theory from which to work. But three groups who are especially interested in serious theories are scientists, mathematicians, and philosophers. These are the groups which place the strictest requirements on the theories they use and construct. While there are important similarities among the kinds of theories dealt with by scientists, mathematicians, and philosophers, there are important differences as well. The most important differences involve the subject matter of the theories. Scientists like to base their theories on experiment and observation of the real world, not on perceptions themselves, but on what they regard as concrete objects of the senses. That is, they like their theories to be empirical. Mathematicians, on the other hand, like their theories to be essentially rational, to be based on logical inference regarding abstract mathematical objects existing in the mind, independently of the senses. And philosophers like to pursue broad theories of reality aimed at relating these two kinds of object. This actually mandates a third kind of object, the infocognitive syntactic operator, but another time. Of the three kinds of theory, by far the lion's share of popular reportage is commanded by theories of science. Unfortunately, this presents a problem. For while science owes a huge debt to philosophy and mathematics, it can be characterized as the child of the former and the sibling of the latter, it does not even treat them as its equals. It treats its parent, philosophy, as unworthy of consideration. And although it tolerates and uses mathematics at its convenience, relying on mathematical reasoning at almost every turn, it acknowledges the remarkable obedience of objective reality to mathematical principles as little more than a cosmic lucky break. Science is able to enjoy its meretricious relationship with mathematics precisely because of its queenly dismissal of philosophy. By refusing to consider the philosophical relationship between the abstract and the concrete on the supposed grounds that philosophy is inherently impractical and unproductive, it reserves the right to ignore that relationship even while exploiting it in the construction of scientific theories. And exploit the relationship it certainly does. There is a scientific platitude stating that if one cannot put a number to one's data, then one can prove nothing at all. But insofar as numbers are arithmetically and algebraically related by various mathematical structures, the platitude amounts to a thinly veiled affirmation of the mathematical basis of knowledge. Although scientists like to think that everything is open to scientific investigation, they have a rule that explicitly allows them to screen out certain facts. This rule is called the scientific method. Essentially, the scientific method says that every scientist's job is to 1. Observe something in the world, 2. Invent a theory to fit the observations, 3. Use the theory to make predictions, 4. Experimentally or observationally test the predictions, 5. Modify the theory in light of any new findings, and 6. Repeat the cycle from step 3 onward. But while this method is very effective for gathering facts that match its underlying assumptions, it is worthless for gathering those that do not. In fact, if we regard the scientific method as a theory about the nature and acquisition of scientific knowledge, and we can, it is not a theory of knowledge in general. It is only a theory of things accessible to the senses. Worse yet, it is a theory only of sensible things that have two further attributes: they are non-universal and can therefore be distinguished from the rest of sensory reality, and they can be seen by multiple observers who are able to replicate each other's observations under like conditions. Needless to say, there is no reason to assume that these attributes are necessary even in the sensory realm. The first describes nothing general enough to coincide with reality as a whole, for example, the homogeneous medium of which reality consists, or an abstract mathematical principle that is everywhere true, and the second describes nothing that is either subjective, like human consciousness, or objective but rare and unpredictable, for example ghosts, UFOs, and Yetis, of which jokes are made but which may, given the number of individual witnesses reporting them, correspond to real phenomena. The fact that the scientific method does not permit the investigation of abstract mathematical principles is especially embarrassing in light of one of its more crucial steps: invent a theory to fit the observations. A theory happens to be a logical and/or mathematical construct whose basic elements of description are mathematical units and relationships. If the scientific method were interpreted as a blanket description of reality, which is all too often the case, the result would go something like this: reality consists of all and only that to which we can apply a protocol which cannot be applied to its own mathematical ingredients and is therefore unreal. Mandating the use of unreality to describe reality is rather questionable in anyone's protocol. What about mathematics itself? The fact is, science is not the only walled city in the intellectual landscape. With equal and opposite prejudice, the mutually exclusionary methods of mathematics and science guarantee their continued separation despite the erstwhile best efforts of philosophy. While science hides behind the scientific method, which effectively excludes from investigation its own mathematical ingredients, mathematics divides itself into pure and applied branches and explicitly divorces the pure branch from the real world. Notice that this makes applied synonymous with impure. Although the field of applied mathematics by definition contains every practical use to which mathematics has ever been put, it is viewed as not quite mathematics and therefore beneath the consideration of any pure mathematician. In place of the scientific method, pure mathematics relies on a principle called the axiomatic method. The axiomatic method begins with a small number of self-evident statements called axioms and a few rules of inference through which new statements, called theorems, can be derived from existing statements. In a way parallel to the scientific method, the axiomatic method says that every mathematician's job is to 1. Conceptualize a class of mathematical objects, 2. Isolate its basic elements, its most general and self-evident principles, and the rules by which its truths can be derived from those principles, 3. Use those principles and rules to derive theorems, define new objects, and formulate new propositions about the extended set of theorems and objects, 4. Prove or disprove those propositions, 5. Where the proposition is true, make it a theorem and add it to the theory, and 6. Repeat from step 3 onwards. The scientific and axiomatic methods are like mirror images of each other, but located in opposite domains. Just replace observe with conceptualize and part of the world with class of mathematical objects, and the analogy practically completes itself. Little wonder, then, that scientists and mathematicians often profess mutual respect. However, this conceals an imbalance. For while the activity of the mathematician is integral to the scientific method, that of the scientist is irrelevant to mathematics, except for the kind of scientist called a computer scientist, who plays the role of ambassador between the two realms. At least in principle, the mathematician is more necessary to science than the scientist is to mathematics. As a philosopher might put it, the scientist and the mathematician work on opposite sides of the Cartesian divider between mental and physical reality. If the scientist stays on his own side of the divider and merely accepts what the mathematician chooses to throw across, the mathematician does just fine. On the other hand, if the mathematician does not throw across what the scientist needs, then the scientist is in trouble. Without the mathematician's functions and equations from which to build scientific theories, the scientist would be confined to little more than taxonomy. As far as making quantitative predictions were concerned, he or she might as well be guessing the number of jellybeans in a candy jar. From this, one might be tempted to theorize that the axiomatic method does not suffer from the same kind of inadequacy as does the scientific method, that it, and it alone, is sufficient to discover all of the abstract truths rightfully claimed as mathematical. But alas, that would be too convenient. In 1931, an Austrian mathematical logician named Kurt Gödel proved that there are true mathematical statements that cannot be proven by means of the axiomatic method. Such statements are called undecidable. Gödel's finding rocked the intellectual world to such an extent that even today, mathematicians, scientists, and philosophers alike are struggling to figure out how best to weave the loose thread of undecidability into the seamless fabric of reality. To demonstrate the existence of undecidability, Gödel used a simple trick called self-reference. Consider the statement, "This sentence is false." It is easy to dress this statement up as a logical formula. Aside from being true or false, what else could such a formula say about itself? Could it pronounce itself, say, unprovable? Let's try it. This formula is unprovable. If the given formula is in fact unprovable, then it is true and therefore a theorem. Unfortunately, the axiomatic method cannot recognize it as such without a proof. On the other hand, suppose it is provable. Then it is self-apparently false, because its provenance-ability belies what it says of itself, and yet true, because provable without respect to content. It seems that we still have the makings of a paradox, a statement that is unprovably provable and therefore absurd. But what if we now introduce a distinction between levels of proof? For example, what if we define a meta-language as a language used to talk about, analyze or prove things regarding statements in a lower-level object language, and call the base level of Gödel's formula the object level and the higher, proof, level the meta-language level? Now we have one of two things: a statement that can be metalinguistically proven to be linguistically unprovable, and thus recognized as a theorem conveying valuable information about the limitations of the object language, or a statement that cannot be metalinguistically proven to be linguistically unprovable, which, though uninformative, is at least no paradox. Voila! Self-reference without paradox. It turns out that this formula is unprovable can be translated into a generic example of an undecidable mathematical truth. Because the associated reasoning involves a meta-language of mathematics, it is called meta-mathematical. It would be bad enough if undecidability were the only thing inaccessible to the scientific and axiomatic methods together. But the problem does not end there. As we noted above, mathematical truth is only one of the things that the scientific method cannot touch. The others include not only rare and unpredictable phenomena that cannot be easily captured by microscopes, telescopes and other scientific instruments, but things that are too large or too small to be captured, like the whole universe and the tiniest of subatomic particles, things that are too universal and therefore indiscernible, like the homogeneous medium of which reality consists, and things that are too subjective, like human consciousness, human emotions, and so-called pure qualities or qualia. Because mathematics has thus far offered no means of compensating for these scientific blind spots, they continue to mark holes in our picture of scientific and mathematical reality. But mathematics has its own problems. Whereas science suffers from the problems just described, those of indiscernibility and induction, non-replicability and subjectivity, mathematics suffers from undecidability. It therefore seems natural to ask whether there might be any other inherent weaknesses in the combined methodology of math and science. There are indeed. Known as the Lowenheim-Skolem theorem and the Duhem-Quine thesis, they are the respective stock in trade of disciplines called model theory and the philosophy of science. Like any parent, philosophy always gets the last word. These weaknesses have to do with ambiguity, with the difficulty of telling whether a given theory applies to one thing or another, or whether one theory is truer than another with respect to what both theories purport to describe. But before giving an account of Lowenheim-Scullum and Duhem Quine, we need a brief introduction to model theory. Model theory is part of the logic of formalized theories, a branch of mathematics dealing rather self-referentially with the structure and interpretation of theories that have been couched in the symbolic notation of mathematical logic, that is, in the kind of mind-numbing chicken scratches that everyone but a mathematician loves to hate. Since any worthwhile theory can be formalized, model theory is a sine qua non of meaningful theorization. Let's make this short and punchy. We start with propositional logic, which consists of nothing but tautological, always true relationships among sentences represented by single variables. Then we move to predicate logic, which considers the content of these sentential variables, what the sentences actually say. In general, these sentences use symbols called quantifiers to assign attributes to variables semantically representing mathematical or real-world objects. Such assignments are called predicates. Next, we consider theories, which are complex predicates that break down into systems of related predicates, the universes of theories, which are the mathematical or real-world systems described by the theories, and the descriptive correspondences themselves, which are called interpretations. A model of a theory is any interpretation under which all of the theory's statements are true. If we refer to a theory as an object language and to its referent as an object universe, the intervening model can only be described and validated in a meta-language of the language universe complex. Though formulated in the mathematical and scientific realms respectively, Lowenheim-Scullum and Duhem Quine can be thought of as opposite sides of the same model theoretic coin. Lowenheim-Scullum says that a theory cannot in general distinguish between two different models. For example, any true theory about the numeric relationship of points on a continuous line segment can also be interpreted as a theory of the integers, counting numbers. On the other hand, Duhem Quine says that two theories cannot in general be distinguished on the basis of any observation statement regarding the universe. Just to get a rudimentary feel for the subject, let's take a closer look at the Duhem Quine thesis. Observation statements, the raw data of science, are statements that can be proven true or false by observation or experiment. But observation is not independent of theory, an observation is always interpreted in some theoretical context. So an experiment in physics is not merely an observation, but the interpretation of an observation. This leads to the Duhem thesis, which states that scientific observations and experiments cannot invalidate isolated hypotheses, but only whole sets of theoretical statements at once. This is because a theory T composed of various laws Li, I equal 1, 2, 3, almost never entails an observation statement except in conjunction with various auxiliary hypotheses Aj, J equal 1, 2, 3. Thus, an observation statement at most disproves the complex Li plus Aj. To take a well-known historical example, let T equal L1, L2, L3 be Newton's three laws of motion, and suppose that these laws seem to entail the observable consequence that the orbit of the planet Uranus is O. But in fact, Newton's laws alone do not determine the orbit of Uranus. We must also consider things like the presence or absence of other forces, other nearby bodies that might exert appreciable gravitational influence on Uranus, and so on. Accordingly, determining the orbit of Uranus requires auxiliary hypotheses like A1 equal only gravitational forces act on the planets, A2 equal the total number of solar planets, including Uranus, is 7, etc. So if the orbit in question is found to differ from the predicted value O, then instead of simply invalidating the theory T of Newtonian mechanics, this observation invalidates the entire complex of laws and auxiliary hypotheses L1, L2, L3, A1, A2. It would follow that at least one element of this complex is false, but which one? Is there any 100% sure way to decide? As it turned out, the weak link in this example was the hypothesis A2 equal the total number of solar planets, including Uranus, is 7. In fact, there turned out to be an additional large planet, Neptune, which was subsequently sought and located precisely because this hypothesis, A2, seemed open to doubt. But unfortunately, there is no general rule for making such decisions. Suppose we have two theories T1 and T2 that predict observations O and not O respectively. Then an experiment is crucial with respect to T1 and T2 if it generates exactly one of the two observation statements O or not O. Duhem's arguments show that in general, one cannot count on finding such an experiment or observation. In place of crucial observations, Duhem cites le bon sens, good sense, a non-logical faculty by means of which scientists supposedly decide such issues. Regarding the nature of this faculty, there is in principle nothing that rules out personal taste and cultural bias. That scientists prefer lofty appeals to Occam's razor, while mathematicians employ justificative terms like beauty and elegance, does not exclude less savory influences. So much for Duhem. Now what about Quine? The Quine thesis breaks down into two related theses. The first says that there is no distinction between analytic statements, for example definitions, and synthetic statements, for example empirical claims, and thus that the Duhem thesis applies equally to the so-called a priori disciplines. To make sense of this, we need to know the difference between analytic and synthetic statements. Analytic statements are supposed to be true by their meanings alone, matters of empirical fact notwithstanding, while synthetic statements amount to empirical facts themselves. Since analytic statements are necessarily true statements of the kind found in logic and mathematics, while synthetic statements are contingently true statements of the kind found in science, Quine's first thesis posits a kind of equivalence between mathematics and science. In particular, it says that epistemological claims about the sciences should apply to mathematics as well, and that Duhem's thesis should thus apply to both. Quine's second thesis involves the concept of reductionism. Reductionism is the claim that statements about some subject can be reduced to, or fully explained in terms of, statements about some, usually more basic, subject. For example, to pursue chemical reductionism with respect to the mind is to claim that mental processes are really no more than biochemical interactions. Specifically, Quine breaks from Duhem in holding that not all theoretical claims, i.e. theories, can be reduced to observation statements. But then empirical observations underdetermine theories and cannot decide between them. This leads to a concept known as Quine's holism, because no observation can reveal which member, S, of a set of theoretical statements should be re-evaluated. The re-evaluation of some statements entails the re-evaluation of all. Quine combined his two theses as follows. First, he noted that a reduction is essentially an analytic statement to the effect that one theory, for example a theory of mind, is defined on another theory, for example a theory of chemistry. Next, he noted that if there are no analytic statements, then reductions are impossible. From this, he concluded that his two theses were essentially identical. But although the resulting unified thesis resembled Duhem's, it differed in scope. For whereas Duhem had applied his own thesis only to physical theories, and perhaps only to theoretical hypotheses rather than theories with directly observable consequences, Quine applied his version to the entirety of human knowledge, including mathematics. If we sweep this rather important distinction under the rug, we get the so-called Duhem-Quine thesis. Because the Duhem-Quine thesis implies that scientific theories are underdetermined by physical evidence, it is sometimes called the underdetermination thesis. Specifically, it says that because the addition of new auxiliary hypotheses, for example conditionals involving if-then statements, would enable each of two distinct theories on the same scientific or mathematical topic to accommodate any new piece of evidence, no physical observation could ever decide between them. The messages of Duhem, Quine and Lowenheim-Scullum are as follows: universes do not uniquely determine theories according to empirical laws of scientific observation, and theories do not uniquely determine universes according to rational laws of mathematics. The model-theoretic correspondence between theories and their universes is subject to ambiguity in both directions. If we add this descriptive kind of ambiguity to ambiguities of measurement, for example the Heisenberg uncertainty principle that governs the subatomic scale of reality, and the internal theoretical ambiguity captured by undecidability, we see that ambiguity is an inescapable ingredient of our knowledge of the world. It seems that math and science are inexact sciences. How, then, can we ever form a true picture of reality? There may be a way. For example, we could begin with the premise that such a picture exists, if only as a limit of theorization, ignoring for now the matter of showing that such a limit exists. Then we could adduce categorical relationships involving the logical properties of this limit to arrive at a description of reality in terms of reality itself. In other words, we could build a self-referential theory of reality whose variables represent reality itself, and whose relationships are logical tautologies. Then we could add an instructive twist. Since logic consists of the rules of thought, i.e. of mind, what we would really be doing is interpreting reality in a generic theory of mind based on logic. By definition, the result would be a cognitive theoretic model of the universe. Gödel used the term incompleteness to describe that property of axiomatic systems due to which they contain undecidable statements. Essentially, he showed that all sufficiently powerful axiomatic systems are incomplete by showing that if they were not, they would be inconsistent. Saying that a theory is inconsistent amounts to saying that it contains one or more irresolvable paradoxes. Unfortunately, since any such paradox destroys the distinction between true and false with respect to the theory, the entire theory is crippled by the inclusion of a single one. This makes consistency a primary necessity in the construction of theories, giving it priority over proof and prediction. A cognitive theoretic model of the universe would place scientific and mathematical reality in a self-consistent logical environment, there to await resolutions for its most intractable paradoxes. For example, modern physics is bedeviled by paradoxes involving the origin and directionality of time, the collapse of the quantum wave function, quantum non-locality, and the containment problem of cosmology. Were someone to present a simple, elegant theory resolving these paradoxes without sacrificing the benefits of existing theories, the resolutions would carry more weight than any number of predictions. Similarly, any theory and model conservatively resolving the self-inclusion paradoxes besetting the mathematical theory of sets, which underlies almost every other kind of mathematics, could demand acceptance on that basis alone. Wherever there is an intractable scientific or mathematical paradox, there is dire need of a theory and model to resolve it. If such a theory and model exist and for the sake of human knowledge, they had better exist. They use a logical meta-language with sufficient expressive power to characterize and analyze the limitations of science and mathematics, and are therefore philosophical and meta-mathematical in nature. This is because no lower level of discourse is capable of uniting two disciplines that exclude each other's content as thoroughly as do science and mathematics. Now here's the bottom line, such a theory and model do indeed exist. But for now, let us satisfy ourselves with having glimpsed the rainbow under which this theoretic pot of gold awaits us. An interdisciplinary approach to reality. 1. General introduction. Since the dawn of our species, human beings have been asking difficult questions about themselves, the universe and the nature of existence, but have lacked a unified conceptual framework strong and broad enough to yield the answers. Enter the cognitive theoretic model of the universe, CTMU. Scientific theories are mental constructs that take objective reality as their content, with the scientific method putting observation first and letting explanation be determined by experiment. But because all theories have logical properties that are abstract and mathematical, and therefore independent of observation, it is these very properties that let us recognize and understand our world. We could equally well start with them and see what they might tell us about objective reality. Just as scientific observation makes demands on theories, the logic of theories makes demands on scientific observation, and these demands tell us in a general way what we can observe about the universe. In other words, a comprehensive theory of reality is not just about observation, but theories and their logical requisites. Since theories are mental constructs, and mental means of the mind, this can be rephrased as follows: mind and reality are linked in mutual dependence on the most basic level of understanding. It is this linkage of the abstract and the concrete, the subjective and the objective, the internal and the external, that constitutes the proper focus of a theory of everything, TO. Since reality forever retains the ability to surprise us, the task of scientific observation can never be completed with absolute certainty, and this means that a comprehensive theory of reality cannot be based on scientific observation alone. Instead, reality theory must be based on the logic underlying the general process of making and interpreting scientific observations. Since observation and interpretation are predicated on the relationship holding between mind and reality, the cognitive theoretic model of the universe delivers an account of that relationship. For the most part, ordinary theories are linguistic and mathematical descriptions of specific observations. In contrast, the CTMU is a meta-theory about the general relationship between theories and observations, i.e., about science, knowledge, and cognition themselves. In explaining this relationship, the CTMU shows that reality possesses a complex property akin to self-awareness. Just as the mind is real, reality is in some respects like a mind. But when we attempt to answer the obvious question whose mind, the answer turns out to qualify by reasonable standards as a mathematical and scientific definition of God. This implies that we all exist in what can be called the mind of God, and that our individual minds are parts of this universal mind. As such, they are directly connected to the greatest source of knowledge and power that exists. This connection of our minds to the mind of the universe, which we sometimes call the soul or spirit, is the most essential part of being human. In its exciting development of these and other ideas, the cognitive theoretic model of the universe helps us to understand not only the nature of reality, but the integral role played by human beings in the creation and maintenance of the world they inhabit. In the process, the CTMU enables us to comprehend the psychological, metaphysical, and ethical ramifications of the relationship between man and the cosmos, and thus what it means to be human. Among the questions that are answered within the framework of the CTMU, what is the nature of humanity's relationship with God? What is our relationship with each other on individual and cultural levels? Do human beings possess free will? Is there life after death? Is there a physical basis for spirituality? Where did the universe come from? Is there such a thing as absolute good or absolute evil? These are just a few of the many burning philosophical dilemmas that mankind has pondered since its infancy. When these dilemmas are finally considered in the advanced conceptual framework of a true tool like the CTMU, their answers fall into place as though under the influence of an attractive force. The mystery melts away, but not the wonder. In its role as a comprehensive theory of reality, the cognitive theoretic model of the universe serves as a firm basis for the unification of science and theology, leading us inevitably in the direction of intellectual enlightenment and a collective spiritual awakening. The traditional Cartesian divider between body and mind, matter and thought, science and spirituality is penetrated by logical reasoning of a higher order than ordinary scientific reasoning, but no less scientific than any other kind of mathematical truth. Accordingly, it serves as the long-awaited gateway between science and humanism, a bridge of reason over what has long seemed an impassable gulf. 2. The CTMU in physics. The avowed goal of physics is to produce what is sometimes called a theory of everything or TOE. As presently conceived, the TOE is thought to consist of one equation describing a single superforce unifying all the forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces. But this is actually an oversimplification. Every equation must be embedded in a theory, and theories require Model S for their proper interpretation. Unfortunately, the currently available theory and model lack three important properties: closure, consistency, and comprehensivity. That is, they are not self-contained, they suffer from various intractable paradoxes, and they conspicuously exclude or neglect various crucial factors, including subjective ones like consciousness and emotion. Since the excluded factors fall as squarely under the heading everything as the included ones, a real TOE has no business omitting them. So as now envisioned by physicists, the TOE is misnamed as a theory of everything. The CTMU, on the other hand, is a TOE framework in which everything really means everything. Whereas the currently envisioned TOE emphasizes objective reality at the expense of its subjective counterpart, mind, the CTMU places mind on the agenda at the outset. It does this not by making assumptions, but by eliminating the erroneous scientific assumption that mind and objective reality can be even tentatively separated. To do this, it exploits not just what we know of objective reality, the so-called everything of the standard TOE, but also what we know of the first word in TOE, namely theory. In other words, it brings the logic of formalized theories to bear on reality theory. Although this is a mathematically obvious move, it has been almost completely overlooked in the physical and mathematical sciences. By correcting this error, the CTMU warrants description as a theory of the relationship between the mind of the theorist and the objective reality about which it theorizes, completing the program of subjective-objective unification already inherent in certain aspects of the formalisms of relativity and quantum mechanics. In the process, it also brings the quantum and classical realms of physics into the sort of intimate contact that can only be provided by a fundamentally new model of physical and metaphysical reality, a model truly worthy of being called a new paradigm. Fundamental to this new model are revisions of basic physical concepts including space, time, matter, and motion. Space, once a featureless medium aimlessly proliferating through cosmic expansion, becomes a distributed syntactic structure iteratively reborn of matter and subject to conspansive evacuation and rescaling. Time, previously envisioned as a quasi-spatial linear dimension along which the cosmos hurtles like a runaway locomotive, becomes the means by which the universe self-configures, an SCSPL grammatical symphony of logico-linguistic transformations played by the self-creating cosmos. Lumps of matter, no longer the inert pawns of external laws of physics, become SCSPL syntactic operators containing within themselves the syntactic rules by which they internally process each other to create new states of physical reality. And motion, once seen as the passage of material attribute ensembles through adjacent infinitesimal cells of empty space displaying them as content, becomes an iterative, self-simulative sequence of endomorphic self-projections by moving bodies themselves. 3. The CTMU in mathematics. Mathematics, like the empirical sciences, requires protection from subjective contamination. Just as the scientific method is designed to exclude bias from science, the axiomatic method is designed to specify an initial set of definitive or self-evident principles and exclude all further assumptions from the deductive process. Accordingly, mathematical entities are objectified by mathematicians in the same way that physical entities are objectified by scientists. They are considered to reside outside the subject, concealed in objective reality as hidden programming or secreted away in an ideal Platonic realm beyond the reach of the senses. Rejecting these notions in absence of a model of reality explicitly relating the mathematical and material worlds, others choose to believe that mathematics is a feature or even an invention of the human mind. But since any meaningful explanation can be logically formalized, and since logic is an essential ingredient of mathematics, subjectivizing mathematics within a Cartesian, dualistic framework would again seem to leave the essential regularities of nature without an objective explanation. Replacing Cartesian dualism with an advanced form of dual-aspect monism, the CTMU treats the abstract and mathematical, and the concrete and physical, as coincident aspects of the same reality. Reality becomes a self-distributed hological system whose essential structure is replicated everywhere within it as mathematical rules of self-recognition and self-processing. Hology, the central attribute of any self-recognizing, self-processing entity, is a logical species of self-similarity according to which such an entity distributes over itself as rules of structure and evolution rules that inhere in, and are obeyed by, every interacting part of the system. Thus, what the system becomes is always consistent with what it already is, and vice versa, its causal integrity is tautologically preserved. In the CTMU, these rules, the syntax of the language spoken to reality by reality itself, are understood to be largely mathematical in nature. The theoretic vantage of the CTMU is essentially logical, with an accent on model theory. Its perspective is associated with the mathematical discipline governing the formulation and validation of theories, namely logic, with emphasis on the branch of logic which deals with the mapping of theories to their universes, namely model theory. This elevates it to a higher level of discourse than ordinary scientific theories, which are simply compact mathematical descriptions of observational data, and even most mathematical theories, which are compact mathematical descriptions of mathematical objects, structures, and processes. This is reflected in the name of the theory. CTMU is just a way of saying the meta-theory that describes a model, or valid interpretation, of the theory of cognition, including logic and mathematics, in the real universe, and vice versa. Since the elementary categories of cognition and perception can be viewed as syntactic elements of cognitive and perceptual languages, cognition and perception can be model-theoretically treated as mappings of cognitive and perceptual languages onto their respective dual universes, and can thus be related by the CTMU within a single monic universe. Because mathematics and science are based on cognition and observation respectively, the CTMU is naturally equipped to address the foundations of both mathematics and science. The CTMU reposes mathematics in reality, and reality in mathematics, in a way that puts each at the other's immediate disposal for solving foundational problems and resolving paradoxes. 4. The CTMU in cosmology. A curious child often asks why questions, and when an answer is given, immediately asks another why question about the answer. Such a child is unsatisfied with superficial explanations, craving instead an ultimate rationale for existence. Example: why is grass green? Chlorophyll's green. Why does grass have chlorophyll? Because it needs to photosynthesize. Why? Because it gets its energy from the sun. Why does the sun make energy? Because it's a huge fusion reactor that takes energy from atoms. Why do atoms have energy? Because, as a man named Einstein showed, matter is energy. Why? Because that's the way the universe is made. What's the universe and who made it? At this point, the weary adult has exhausted his scientific knowledge and must begin to deal with the most general and philosophically controversial abstractions in his mental vocabulary or give up. Stephen Hawking is among those who have proposed a way out of the regress. In collaboration with James Hartle, he decided to answer the last question, what is the universe and who made it? As follows. The universe made itself, and its structure is determined by its ability to do just that. This is contained in the no-boundary proposal, which Hawking describes thusly: this proposal incorporates the idea that the universe is completely self-contained, and that there is nothing outside the universe. In a way, you could say that the boundary conditions of the universe are that there is no boundary. To mathematically support this thesis, Hawking infuses the quantum wave function of the universe with a set of geometries in which space and time are on a par. The fact that time consists of a succession of individual moments thus becomes a consequence of spatial geometry, explaining the arrow of time by which time flows from past to future. Unfortunately, despite the essential correctness of the intrinsic cosmology idea, to make the universe self-contained and self-explanatory, there are many logical problems with its execution. These problems cannot be solved simply by choosing a convenient set of possible geometries, structurings of space. One must also explain where these geometric possibilities came from. For his own part, Hawking explains them as possible solutions of the equations expressing the laws of physics. But if this is to be counted a meaningful explanation, it must include an account of how the laws of physics originated, and there are further requirements as well. They include the need to solve paradoxical physical conundrums like ex nihilo cosmogony, how something, namely the universe, can be created from nothing, quantum non-locality, how subatomic particles can instantaneously communicate in order to preserve certain conserved physical quantities, accelerating cosmic expansion, how the universe can appear to expand when there is no external medium of expansion, and accelerate in the process to boot, and so on. Even in the hands of experts, the conventional picture of reality is too narrow to meaningfully address these issues. Yet it is too useful, and too accurate, to be wrong. In light of the fundamentality of the problems just enumerated, this implies a need for additional logical structure, with the extended picture reducing to the current one as a limiting case. The CTMU takes the reflexive self-containment relationship invoked by Hawking and some of his cosmological peers and predecessors and explores it in depth, yielding the logical structures of which it is built. Together, these structures comprise an overall structure called SCSPL, acronymic for Self-Configuring Self-Processing Language. The natural terminus of the cosmological self-containment imperative, SCSPL, is a sophisticated mathematical entity that possesses logical priority over any geometric explanation of reality, and thus supersedes previous models as a fundamental explanation of the universe we inhabit. In doing so, it relies on a formative principle essential to its nature, the Tillich principle. A logical analog of teleology, the Tillich principle replaces the usual run of ontological hypotheses, including quasi-tautological anthropic principles such as "we perceive this universe because this universe supports our existence," as the basis of cosmogony. 5. The CTMU and modern philosophy. 20th century philosophy has been dominated by the linguistic and logico-analytic schools, whose joint program was to convert concepts and observations to language, and scientific and philosophical reasoning to the logical analysis of language. As long as language was by assumption held apart from reality, this program had the inevitable and unfortunate effect of demoting philosophy to the status of an irrelevant word game. In consequence, philosophers have lapsed into a pervasive cynicism that eats away at the foundations of human knowledge like a slow cancer, looking resignedly to scientific materialism to solve problems that science itself has frankly admitted are philosophical and empirically unsolvable. Perceiving themselves as hopelessly beaten in the name of philosophy, the vast majority of modern philosophers have dejectedly become traitors to their cause. The CTMU ignores philosophical defeatism and takes the obvious next step in the logico-linguistic tradition, which is to subject the problematic relationship between language and reality itself to logical analysis. When this is properly done, it turns out that reality and language are not so easily held apart. In fact, it turns out that they can ultimately be treated as identical for purposes of philosophical and scientific reasoning, that they can be melded in a single self-similar medium, SCSPL, which is everywhere both real and linguistic, i.e., monic and CTMU dual aspect sense, as distinguished from the separative dualism pervading the sciences. This restores philosophy to a position from which it can effect the resolution of scientific paradox, which is just what the CTMU does in its capacity as reality theory. More specifically, because it comprises a higher-level meta-language of the language of physics, the CTMU is technically a theory of metaphysics in the formal sense. A meta-language is a higher-level language in which one can talk about the structure of a lower-level language and its correspondence to whatever it describes. Thus, it has bearing on the traditional ingredients of metaphysics, including cosmology, the study of the origin and composition of the universe, ontology, the study of being, and epistemology, the study of the nature and limits of knowledge. The CTMU is thus closely related not only to cosmological science, but also to the burgeoning philosophies of mind and language. 6. The CTMU and theology. Basically, the scientific method says that science should be concerned with objective phenomena meeting at least two criteria: distinguishability, which means that they produce distinctive effects, and replicability, which means that they can be experimentally recreated and studied by multiple observers who compare their data and confirm each other's findings. Unfortunately, God nowhere fits into this scheme. First, God is considered to be omnipresent even in monotheistic schemata, which means distributed over reality as a whole and therefore lacking any specific location at which to be distinguished. Second, there is such a thing as being too replicable. If something is distributed over reality, then it is present no matter where or when it is tested, and one cannot distinguish what is being replicated. And then, of course, we have the creator aspect of God. If God is indeed the creator of reality, then he need not make his works replicable by mere scientists. Thus, the God concept is unavoidably ambiguous in both spatial and temporal location, and no amount of scientific experimentation can overcome this logical difficulty. In short, while the God concept may be amenable to empirical confirmation, for example through the discovery of vanishingly improbable leaps of biological evolution exceeding available genetic information, it is by definition resistant to scientific verification. God, like consciousness, is a predicate whose extended logical structure, including a supporting conceptual framework, exceeds what science is presently equipped to analyze. This, of course, means that arguments for or against God cannot be decided on empirical grounds, all but precluding a working relationship between the scientific and religious communities. Even the sincerest attempts to foster dialogue between the two camps are obstructed by the unrealistic expectations of each regarding the ability of the other to meet it on its own ground, whereas the obvious first step towards meaningful communication is a basis for mutual understanding. No amount of encouragement or monetary incentive can provide it for those whose languages stubbornly resist translation. Since this describes the relationship between science and religion, the first step toward reconciliation must be to provide a logical bridge between their internal languages, a master language in which both languages are embedded. The CTMU, conceived as the most general and comprehensive of logical languages, is designed to serve as that bridge. It has been written that God is dead. This might more accurately have been written about faith. Mankind is creating an increasingly complex and mechanized world, and the essence of complexity and mechanism is not faith, but logic. So the time for a logical approach to theology is nigh. Accordingly, the CTMU does not begin with a preconceived definition of God, rather, it determines within the extended logical structure of reality how the properties most often attributed to God are logically related, reserving the title for the relationship actually adduced. In this way, it avoids the circular, faith-driven explanations to which religion so often resorts, and at which science so often revolts. And meanwhile, by eliminating the barrier between subjective and objective reality, it permits recognition of the subjective dimension of the universe as a whole, the dimension by virtue of which the universe can truly be described as the mind of God. 7. The CTMU and teleology. Historically, the telic principle can be understood as a logical analog of teleology, incorporating John Archibald Wheeler's observer participation thesis. Approximately, man participates in the ongoing quantum-scale creation of reality by observing it and thereby collapsing the wave function representing its potential. More directly, the telic principle says that reality is a self-configuring entity that emerges from a background of unbound potential as a protean recursive construct with a single imperative: self-actualization. In other words, existence and its amplification is the tautological raison d'être of the cosmos. The phrase raison d'être has a literal significance. In order to exist, a self-contained universe must configure itself to recognize its own existence, and to configure itself in this way it must, by default, generate and parameterize its own self-configuration and self-recognition functions. This describes a situation in which the universe generates its own generalized utility. To self-configure, the universe must have a self-actualization criterion by which to select one of many possible structures or futures for itself, and this criterion is a generalized analog of human utility, its raison d'être. In addition to generalized utility and generalized volition, teleology, the universe also possesses generalized cognition, coherent self-recognition. By any reasonable definition of the term mental, this makes the universe mental in a generalized sense, where generalized means that these attributes conform to general functional descriptions of what humans do in the process of volition, cognition, and mentation. The coherent self-recognition feature of reality appears as an explicit feature of conspansive space-time, a model-theoretic dual of the expanding cosmos. Whereas the expanding cosmos is simplistically depicted in terms of a model called ERSU, short for expanding rubber sheet universe, conspansive space-time is depicted by a model-theoretic dual of ERSU called USRE, short for the universe as a self-representational entity. While ERSU is a product of Cartesian mind-matter dualism that effectively excludes mind in favor of matter, USRE, which portrays the universe as a self-simulation, is a form of dual-aspect monism according to which reality is distributively informational and cognitive in nature. It is important to understand that the CTMU does not arbitrarily project human attributes onto the cosmos. It permits the logical deduction of necessary general attributes of reality, lets us identify any related human attributes derived from these general attributes, and allows us to explain the latter in terms of the former. CTMU cosmology is thus non-anthropomorphic. Rather, it uses an understanding of the cosmological medium of sentience to explain the mental attributes inherited by sentient organisms from the cosmos in which they have arisen. Unlike mere anthropomorphic reasoning, this is a logically correct description of human characteristics in terms of the characteristics of the universe from which we derive our existence. 8. The CTMU and consciousness studies. Modern science seems to offer many intriguing clues about the nature of consciousness, mainly involving the structure and dynamics of the brain. But for all its success and sophistication, science is ill-equipped to turn these clues into an ultimate explanation of consciousness or any other subjective property. Among the reasons are its empiricism, which means that it prefers observation to introspection, its objectivism, which means that it deliberately excludes subjective contamination from that which is observed, and its physical reductionism, which means that it tries to account for all scientific observations strictly in terms of matter and energy distributed in space and time. Unfortunately, this perspective is innately opposed to the study of anything that is subjective by nature, i.e., any property not directly observable except by the mind that embodies it. In its zeal to eliminate subjective contamination, science unwittingly discards the baby with the bathwater. As an example of the scientific perspective, consider the Turing test, a version of which says that the humanoid consciousness of a machine intelligence can only be tested by letting it hold an anonymous conversation with a real human. If the human is fooled into thinking that he is conversing with another human, then the machine is taken to possess human consciousness. But in fact, all that such a machine has demonstrated are certain objective effects usually associated with the property consciousness, but which may have been mindlessly produced by a set of logical instructions executed by inanimate hardware. The only thing that knows whether the machine is truly conscious is the machine itself, and only if it is truly conscious at that. For its own part, science lacks the conceptual apparatus to even make this distinction. Unfortunately, philosophy, the mother of science, appears to have abdicated its parental responsibility, failing to tell science how to enlarge its horizons to accommodate subjective phenomena. The CTMU fills this breach, using advanced logic to expand our conceptual framework in a way that permits the meaningful analysis of subjective properties. It does this by enlarging and deepening the relationship between the most fundamental ingredients of scientific analysis, ingredients like space, time, and object, and developing the implications in a mathematical and scientific context. The explanations that emerge not only possess an unprecedented degree of logical structure, but are automatically integrated with science and compatible with all of its best insights. 9. The CTMU and intelligent design. Among the most exciting recent developments in science are complexity theory, the theory of self-organizing systems, and the modern incarnation of intelligent design theory, which investigates the deep relationship between self-organization and evolutionary biology in a scientific context not preemptively closed to theological causation. Bucking the traditional physical reductionism of the hard sciences, complexity theory has given rise to a new trend, informational reductionism, which holds that the basis of reality is not matter and energy, but information. Unfortunately, this new form of reductionism is as problematic as the old one. As mathematician David Berlinski writes regarding the material and informational aspects of DNA, we quite know what DNA is, it is a macromolecule and so a material object. We quite know what it achieves, apparently everything. Are the two sides of this equation in balance? More generally, Berlinski observes that since the information embodied in a string of DNA or protein cannot affect the material dynamic of reality without being read by a material transducer, information is meaningless without matter. The relationship between physical and informational reductionism is a telling one, for it directly mirrors Cartesian mind-matter dualism, the source of several centuries of philosophical and scientific controversy regarding the nature of deep reality. As long as matter and information remain separate, with specialists treating one as primary while tacitly relegating the other to secondary status, dualism remains in effect. To this extent, history is merely repeating itself, where mind and matter once vied with each other for primary status, concrete matter now vies with abstract information, abstractly representing matter and its extended relationships. But while the abstractness of information seems to make it a worthy compromise between mind and matter, Berlinski's comment demonstrates its inadequacy as a conceptual substitute. What is now required is thus what has been required all along, a conceptual framework in which the relationship between mind and matter, cognition and information, is made explicit. This framework must not only permit the completion of the gradual ongoing dissolution of the Cartesian mind-matter divider, but the construction of a footworthy logical bridge across the resulting explanatory gap. Mathematically, the theoretical framework of intelligent design consists of certain definitive principles governing the application of complexity and probability to the analysis of two key attributes of evolutionary phenomena: irreducible complexity and specified complexity. On one hand, because the mathematics of probability must be causally interpreted to be scientifically meaningful, and because probabilities are therefore expressly relativized to specific causal scenarios, it is difficult to assign definite probabilities to evolutionary states in any model not supporting the detailed reconstruction and analysis of specific causal pathways. On the other hand, positing the absolute improbability of an evolutionary state ultimately entails the specification of an absolute, intrinsic global model with respect to which absolute probabilistic deviations can be determined. A little reflection suffices to inform us of some of its properties. It must be rationally derivable from a priori principles and essentially tautological in nature, it must on some level identify matter and information, and it must eliminate the explanatory gap between the mental and physical aspects of reality. Furthermore, in keeping with the name of that to be modeled, it must meaningfully incorporate the intelligence and design concepts, describing the universe as an intelligently self-designed, self-organizing system. The CTMU is exactly the model required. It describes reality as a self-configuring self-processing language, an ultimate kind of self-organizing, self-emergent system consisting of infocognitive syntactic operators at once material and informational in nature. It is a rationally bootstrapped model theoretic extension of logic that shares its tautological structure, approximating an answer for Berlinski's question, what brings a universe into being? Owing to conspansion, a distributed evolutionary process by virtue of which the universe can be described as a universal self-representational entity, it unites mind and matter in a self-configuring, self-processing system endowed with a species of coherence substantiating its possession of higher-order sentience. And last but not least, it puts everything under the control of a logical analog of teleology called the telic principle, conspansively adjoining to the laws of physics an extended superposition principle that provides irreducible and specified complexity with a mechanism they would otherwise have continued to lack. 10. Summary, the bottom line. To summarize, the CTMU is a theory of reality as mind, in principle spanning all of science while permitting a logical analysis of consciousness and other subjective predicates. This does not mean that it has solved all of the problems of science and the philosophy of mind, but only that it has laid the preliminary groundwork. It provides the logical framework of a TOE, yielding an enhanced model of space-time, affording preliminary explanations of cosmogony, accelerating cosmic expansion, quantum non-locality, the arrow of time, and other physical and cosmological riddles that cannot be satisfactorily explained by other means. The CTMU penetrates the foundations of mathematics, describing the syntactic relationships among various problematic mathematical concepts in a reality-theoretic context. It is the culmination of the modern logico-linguistic philosophical tradition, reuniting the estranged couple consisting of rationalistic philosophy and empirical science. It provides an indispensable logical setting for intelligent design. And perhaps most importantly, the CTMU enables a logical description of God and an unprecedented logical treatment of theology, comprising a metaphysical framework in which to unite people of differing faiths and resolve religious conflicts. On absolute truth and knowledge. First, a word on the title of this essay. Absolute knowledge is absolutely true, and absolute truth is the definitive predicate of absolute knowledge. That is, if something is known with absolute certainty, then it can be subjected to tests affirming its truth, while if something can be affirmatively tested for truth, then it is known with certainty by the tester. This applies whether the tests in question are perceptual or inferential. Where knowledge can denote either direct embodiment or internal modeling by an arbitrary system, and test denotes a straightforward systemic efficacy criterion, knower and tester can refer to reality at large. In this generalization, truth and knowledge are identical. While it is possible to split, splice and braid countless philosophical hairs over the connotations respectively attached to truth and knowledge, this simple generalized relationship conveniently spares us the necessity. It is with this express understanding that these terms and phrases are employed herein. To perceive one and the same reality, human beings need a kind of absolute knowledge wired into their minds and nervous systems. The structure and physiology of their brains, nerves, and sense organs provide them, at least in part, with elementary cognitive and perceptual categories and relationships in terms of which to apprehend the world. This absolute kind of knowledge is what compels the perceptions and logical inferences of any number of percipients to be mutually consistent, and to remain consistent over time and space. Without the absoluteness of such knowledge, without its universality and invariance, we could not share a common reality, our minds and senses would lie and bicker without respite, precipitating us into mental and sensory chaos. Time and space, mind and matter, would melt back into the haze of undifferentiated potential from which the universe is born. Given the fact that absolute knowledge is a requisite of our collective ability to sustain a perceptually consistent universe, it is nothing short of astonishing that there are people who react with incredulity or derision at any mention of its possible existence. Their attitude seems to be that the very idea smacks of hubris, being nothing but an empty pretense exceeding the capacity of the small and overly challenged human mind. The truth, however, is that hubris is nowhere more evident than among those holding irrational opinions in contempt of logic, and denying the existence of absolute knowledge is a case in point. In fact, the entire history of philosophy and science can be characterized as an undying quest for absolute knowledge, a timeless attempt to comprehensively extend the a priori and analytical into the realm of the apparently a posteriori and synthetic. This quest includes the efforts of researchers from many fields, from physics and cosmology to philosophy and computer science. The holy grail of this quest is known as the TO, or theory of everything. A TO purports to be absolute truth by an implicit reductio ad absurdum. If it does not constitute absolute truth, then its truth can be relativized to a partial context within reality at large, in which case it is not a theory of everything. Thus, if a TO exists, it falls squarely under the heading of absolute knowledge. But unfortunately, the proper method for constructing such a theory has not been entirely obvious, particularly to theorists steeped in the ambiguities and paradoxes of 4 centuries of post-Cartesian science and philosophy. As science has advanced and philosophy has wearily tried to keep pace, their once stentorian claims of absolute truth have been all but extinguished, and the mainstream search for a TO has lately been pursued without a clear understanding of what is being sought. The apparent absence of a TO notwithstanding, has any kind of absolute knowledge ever been scientifically formulated? Yes, in the form of logical tautologies. A tautology is a sentential relation, i.e. a formula consisting of variables and logical connectives, with the property that it is true for all possible assignments of Boolean truth values, true or false, to its variables. For example, the statement if X is a sentence, then either X or not X, but not both, must be true is a tautology because no matter which truth values are consistently applied to X and not X, the statement is unequivocally true. Indeed, tautologies comprise the axioms and theorems of two-valued logic itself, and because all meaningful theories necessarily conform to two-valued logic, define the truth concept for all of the sciences. From mathematics and physics to biology and psychology, logical tautologies reign supreme and inviolable. That a tautology constitutes absolute truth can be proven as follows. First, logic is absolute within any system for which, a, the complementary truth values t, true, and f, false, correspond to systemic inclusion and exclusion, a semantic necessity without which meaningful reference is impossible, and b, lesser predicates and their complements equal subsystemic inclusion and exclusion. Because a tautology is an axiom of two-valued logic, violating it disrupts the T/F distinction and results in the corruption of informational boundaries between perceptual and cognitive predicates recognized or applied in the system, as well as between each predicate and its negation. Thus, the observable fact that perceptual boundaries are intact across reality at large implies that no tautology within its syntax, or set of structural and functional rules, has been violated. Indeed, if such a tautology ever were violated, then reality would disintegrate due to corruption of the informational boundaries which define it. So a tautology is absolute truth not only with respect to logic, but with respect to reality at large. What does this mean? Uncertainty or non-absoluteness of truth value always involves some kind of confusion or ambiguity regarding the distinction between the sentential predicates true and false. Where these predicates are applied to a more specific predicate and its negation, for example, it is true that the earth is round and false that the earth is not round, the confusion devolves to the contextual distinction between these lesser predicates, in this case round and not round within the context of the earth. Because all of the ambiguity can be localized to a specific distinction in a particular context, it presents no general problem for reality at large. We can be uncertain about whether or not the earth is round without disrupting the logic of reality in general. However, where a statement is directly about reality in general, any disruption of or ambiguity regarding the T/F distinction disrupts the distinction between reality and not reality. Were such a disruption to occur at the level of basic cognition or perception, reality would become impossible to perceive, recognize, or acknowledge as something that exists. By definition, this is the case with regard to our cognitive perceptual syntax, the set of structural and inferential rules governing perception and cognition in general. Since a tautology is a necessary and universal element of this syntax, tautologies can under no circumstances be violated within reality. Thus, they are absolute knowledge. We may not be able to specify every element of absolute knowledge, but we can be sure of two things about it: that it exists in reality to the full extent necessary to guarantee its non-violation, and that no part of it yet to be determined can violate absolute knowledge already in hand. Whether or not we can write up an exhaustive itemized list of absolute truths, we can be sure that such a list exists, and that its contents are sufficiently recognizable by reality at large to ensure their functionality. Absolute truth, being essential to the integrity of reality, must exist on the level of reference associated with the preservation of global consistency, and may thus be duly incorporated in a theory of reality. On the other hand, the fact that any reasonable definition of absolute truth amounts to tautology can be shown by reversing this reasoning. Since absolute truth must be universal, it is always true regardless of the truth values of its variables, where the variables actually represent objects and systems for which specific state descriptions vary in space and time with respect to truth value. Moreover, it falls within its own scope and is thus self-referential. By virtue of its universality and self-reference, it is a universal element of reality syntax, the set of structural and functional rules governing the spatial structure and temporal evolution of reality. As such, it must be unfalsifiable, any supposition of its falsehood leading directly to a reductio ad absurdum. And to ice the cake, it is unavoidably implicated in its own justification. Were it ever to be violated, the T/F boundary would be disrupted, and this would prevent it, or anything else, from being proven. Therefore, it is an active constraint in its own proof, and thus possesses all the characteristics of a tautology. To recap, the characteristic attributes of a logical tautology are as follows: 1. It cannot be disobeyed, which implies that it has universal scope and thus accepts and truthfully predicates all closed sentential, predicative, structures, including itself and logic in its entirety, under assignment to its own variables, and 2. It is self-affirming or self-justifying and figures in its own definition or demonstration within the associated grammar. Obviously, 1 and 2 are not independent. 1 implies that a tautology is a universal, self-similar, metalogical element of syntax of the language and metalanguages of which it is a part, while 2 says that it is a critical element of syntax that cannot be eliminated without compromising the integrity of the syntax as a whole. Thus, any supposition that it is false or eliminable reduces itself to absurdity by syntactic rules of inference, forcing the syntax to protect itself through reductio ad absurdum. Since any reasonable syntactic and/or semantic definition of absolute truth bestows upon it the properties of necessity and truthwise invariance with respect to content, it is unquestionably tautological in nature. Accordingly, it is desirable to formulate reality theory as a tautology. To whatever extent this can be done, the theory constitutes absolute knowledge and is therefore eligible as a TO. This suffices to show that if the form of absolute knowledge hopefully referred to as a TO exists, it must be tautological. Next we will show that a TO and its universe can be related in such a way that the theory is semantically tautological with respect to its universe, i.e. that, a. the theory is intrinsically tautological, and, b. its tautological structure is modeled by its universe. And in the course of doing so, we will show that it is indeed possible to ensure by the method of constructing this theory that its universe coincides with reality at large, and thus that it constitutes a valid theory of reality. Specifically, the construction will incorporate one or more attributes that are necessarily modeled by reality at large, and that simultaneously ensure the theory's tautological structure. How can a TO, or comprehensive theory of reality, be structured as a tautology? First, by definition, a TO is universal. This is implied by the E, which stands for everything. Thus, it is comprehensive. Second, it is self-referential. A theory of everything, being a part of the everything to which it refers, must refer to itself. More precisely, a TO must be totally recursive in a manner analogous to logic, each atom referring exclusively to other parts of the theory, and be able to refer to itself in part and in whole in order to possess full logical closure. This can be arranged by incorporating one or more self-representative variables and their definitive relationships, up to and including a dynamic variable representing the theory as a whole. In fact, the theory can incorporate a homology predicate that goes considerably farther. Instead of merely containing itself as a variable, a theory equipped with such a predicate can everywhere contain itself by virtue of self-similarity or self-distribution. Because it represents a theory of perceptual reality, this variable contains all elements of cognitive syntax and their perceptual contents. Since variables can be defined in general terms without specifically enumerating their contents, we do not need to know exactly what it contains in order to use it. And third, because logic is the primary ingredient of cognitive perceptual syntax, the self-referential TO refers to logic in part and in whole and is therefore metalogical. Thus, it can incorporate a kind of ultimate truth predicate that asserts its own tautological structure and guarantees that no matter what, semantic and other, kinds of paradox may arise within the theory, they can always be resolved within the theory. A theory possessing all three of these properties is called a supertautology, denoting the reality-theoretic counterpart of a logical tautology. Let us now attend to some of the details of constructing a supertautology. First, we repose the a priori and analytic knowledge that we are given in the form of cognitive syntax, including logic and all of its implications, in a variable to which we apply, a. the rules of logic itself, b. three recursively related metalogical axioms that are themselves true a priori and analytically implied by each other, in a word, self-evident. Note again that in creating and assigning content to this variable, we do not have to enumerate all of its contents, we can refer to them en masse by their joint characteristic, namely the absoluteness necessary to ensure perceptual and inferential consistency. Since a theory falls under the mathematical definition of a language, it is natural to refer to the contents in question as the rules of syntax of that language, or simply as its syntax. Thus, the TO recursively contains a variable representing its own syntax, permitting the manipulation of that variable and the grammatical extraction of its implications according to syntactic rules. This recursive construction makes the absoluteness of the variable, and theory, logically heritable, conferring absoluteness on whatever is inferred within the system. Together, the implicate variable and its explicate theoretic medium comprise a bootstrapped extension of the self-referential syntax of logic itself, letting that syntax be mined for a potential wealth of hidden analytic content. The key to applying this knowledge scientifically is the semantic functionality of the three metalogical axioms adjoining the object-level syntax. Conveniently, these, recursively related, axioms can be thought of in terms of a trio of property-principal pairs, the 3 CS and the 3 MS. The CS are three properties that a TO must inevitably possess, namely comprehensiveness, closure and consistency, while the MS are metalogical axioms respectively associated with those properties. These principles are the mind equals reality principle, associated with comprehensiveness, the metaphysical autology principle, associated with closure, and the multiplex unity principle, associated with consistency, respectively abbreviated M=R, MAP, and μ. We have already been partially introduced to these principles in all but name, and in any case need only one of them to proceed farther, M=R. Concisely, M=R asserts that there exists a semantic, language to universe, correspondence between objective reality and the absolute subjective rules of perception and inference, i.e. cognitive and perceptual syntax. This correspondence defines a morphism, incoversion, predicating the assignment of a certain structural predicate, hology, to the universe language/meta-language system, see Introduction to the CTMU. Hology, a special kind of self-similarity conferring supertautological status, equals the relationship of the TOE and its universe to the self-representative variable by which it is encapsulated. Hology means that the syntax by which reality configures, recognizes, and processes itself is the image of a distributed endomorphism, the incoversion morphism, surjecting the objective self-intersect, distributed component, of reality onto every interior point and region of reality as transductive syntactic potential, i.e. as general rules of transduction to be variously expressed by objects at any location. Although real objects generally access and express only a small part of this syntax, combinations of interacting objects may express and access more of it by mutual input-to-output behavioral transduction. Through this kind of behavioral transduction, the self-intersect, though generally composed of distributed rules applying everywhere in reality, resolves to a distributed conditional form, DCF, explicitly containing all of the local systems and states generated by those rules. The self-intersect and its DCF resolution comprise the syntax and language of reality. Because hology maps the reality syntax to our cognitive syntax, because the self-intersect plays dual objective and subjective roles, perceptible objects and processes tautologically conform to our innate perceptual categories, making the TOE a supertautology comprising the purest and most universal kind of absolute truth. The above reasoning subjects the absolute, a priori, knowledge in our minds to a kind of recursive squaring operation, causing it to self-explicate as its own medium and projecting it onto external reality. This repetitive operation resembles the mutual reflection of a pair of polymorphic mirrors, one labeled mind and the other labeled reality, that faithfully reflect each other's evolving image. Although one might suspect that the tautological nature of the construction renders it barren of interest, this would be akin to saying that a squaring operation never yields more than the original number. While that might be true for a featureless numeric identity, for example 12 = 1, the cognitive syntax of the human mind is far from featureless. In recursive self-combination, it is capable of generating a universe, and a theory constructed according to this recursive relationship is capable of veridically capturing that universe. Indeed, there is a sense in which the TOE, and all of the absolute knowledge it holds, is identical to the universe it describes. But the meaning of this statement, and it is a statement that is pregnant with meaning, lies beyond the purpose at hand. The CTMU is a theory of reality, or TOE, that has been constructed according to this blueprint. If, as a rationalist, one insists that absolute truth and knowledge are exclusively mathematical, then the CTMU is mathematics. If, as an empiricist, one insists that they reside exclusively in our direct perceptions of reality, then the CTMU is embodied in our direct perceptions of reality, including our direct perceptions of the comprehensiveness, closure, and consistency of reality. The truth, of course, is that by the method of its construction, it is both. But in any case, would-be pundits who cling blindly to folk epistemological absolutes like truth is never more than provisional, science is inherently without stability and there are no such things as absolute truth and knowledge are urgently in need of an intellectual awakening, and until it comes, should refrain from disseminating their irrational opinions to others who might gullibly mistake them for fact. Such truisms have their contexts, but these contexts do not include the highest levels of discourse regarding truth and knowledge, and they do not include the CTMU. There is, of course, more to the CTMU than just its supertautological structure. For example, it incorporates a new conceptualization of space-time, resolves numerous high-level reality theoretic paradoxes, and establishes a bridge between science and theology, all with considerably more detail than this brief monograph allows. But as regards absolute truth and knowledge, its status as a supertautology is necessary and sufficient to explain why it is uniquely qualified for the title. If the simplicity and elegance of its design seems too obvious, too convenient or too good to be true, this is certainly no fault of the theory or its author. At best, it testifies to the opacity of certain formerly useful but outworn conceptual barriers erected in science and philosophy over the last several centuries, and to the inertia of the scientific and academic establishments which tend them. One final note. The CTMU is neither intended nor presented as an encyclopedic compendium of absolute truth. It is meant only to provide a comprehensive, consistent and self-contained, and to that extent absolute, logical framework for bridging the gaps between apparently unrelated fields of knowledge, helping to locate and correct fundamental inconsistencies within and among these fields, and developing new kinds of knowledge that might arise from the intersections of fields which already exist. Because the real universe is everywhere in the process of self-creation, human knowledge can and must continue to grow. The CTMU is intended not as a brittle, undersized pot that will root bind and choke this growing knowledge, but as fertile and well-aerated soil through which it can spread. By its very design, the CTMU will continue to accommodate and accelerate our intellectual progress, and since there is no other theory that fully shares its design, it is irreplaceable for that purpose. This completes our introduction to the topic of absolute truth and knowledge. Introduction to the CTMU. The real universe has always been theoretically treated as an object, and specifically as the composite type of object known as a set. But an object or set exists in space and time, and reality does not. Because the real universe by definition contains all that is real, there is no external reality, or space, or time, in which it can exist or have been created. We can talk about lesser regions of the real universe in such a light, but not about the real universe as a whole. Nor, for identical reasons, can we think of the universe as the sum of its parts, for these parts exist solely within a space-time manifold identified with the whole and cannot explain the manifold itself. This rules out pluralistic explanations of reality, forcing us to seek an explanation at once monic, because non-pluralistic, and holistic, because the basic conditions for existence are embodied in the manifold, which equals the whole. Obviously, the first step towards such an explanation is to bring monism and holism into coincidence. When theorizing about an all-inclusive reality, the first and most important principle is containment, which simply tells us what we should and should not be considering. Containment principles, already well known in cosmology, generally take the form of tautologies. For example, the physical universe contains all and only that which is physical. The predicate physical, like all predicates, here corresponds to a structured set, the physical universe. Because the universe has structure and contains objects, it is a structured set. But this usage of tautology is somewhat loose, for it technically amounts to a predicate logical equivalent of propositional tautology called autology, meaning self-description. Specifically, the predicate physical is being defined on topological containment in the physical universe, which is tacitly defined on and descriptively contained in the predicate physical, so that the self-definition of physical is a two-step operation involving both topological and descriptive containment. While this principle, which we might regard as a statement of physicalism, is often confused with materialism on the grounds that physical equals material, the material may in fact be only a part of what makes up the physical. Similarly, the physical may only be a part of what makes up the real. Because the content of reality is a matter of science as opposed to mere semantics, this issue can be resolved only by rational or empirical evidence, not by assumption alone. Can a containment principle for the real universe be formulated by analogy with that just given for the physical universe? Let's try it. The real universe contains all and only that which is real. Again, we have a tautology, or more accurately an autology, which defines the real on inclusion in the real universe, which is itself defined on the predicate real. This reflects semantic duality, a logical equation of predication and inclusion whereby perceiving or semantically predicating an attribute of an object amounts to perceiving or predicating the object's topological inclusion in the set or space dualistically corresponding to the predicate. According to semantic duality, the predication of the attribute real on the real universe from within the real universe makes reality a self-defining predicate, which is analogous to a self-including set. An all-inclusive set, which is by definition self-inclusive as well, is called the set of all sets. Because it is all-descriptive as well as self-descriptive, the reality predicate corresponds to the set of all sets. And because the self-definition of reality involves both descriptive and topological containment, it is a two-stage hybrid of universal autology and the set of all sets. Now for a brief word on sets. Mathematicians view set theory as fundamental. Anything can be considered an object, even a space or a process, and wherever there are objects, there is a set to contain them. This something may be a relation, a space, or an algebraic system, but it is also a set. Its relational, spatial or algebraic structure simply makes it a structured set. So mathematicians view sets, broadly including null, singleton, finite and infinite sets, as fundamental objects basic to meaningful descriptions of reality. It follows that reality itself should be a set, in fact, the largest set of all. But every set, even the largest one, has a power set which contains it, and that which contains it must be larger, a contradiction. The obvious solution: define an extension of set theory incorporating two senses of containment which work together in such a way that the largest set can be defined as containing its power set in one sense while being contained by its power set in the other. Thus, it topologically includes itself in the act of descriptively including itself in the act of topologically including itself, and so on, in the course of which it obviously becomes more than just a set. In the cognitive theoretic model of the universe or CTMU, the set of all sets, and the real universe to which it corresponds, take the name, SCSPL, of the required extension of set theory. SCSPL, which stands for self-configuring self-processing language, is just a totally intrinsic, i.e. completely self-contained, language that is comprehensively and coherently, self-distributively, self-descriptive, and can thus be model-theoretically identified as its own universe or referent domain. Theory and object go by the same name because unlike conventional ZF or NBG set theory, SCSPL hologically infuses sets and their elements with the distributed, syntactic, metalogical, component of the theoretical framework containing and governing them, namely SCSPL syntax itself, replacing ordinary set theoretic objects with SCSPL syntactic operators. The CTMU is so named because the SCSPL universe, like the set of all sets, distributively embodies the logical syntax of its own descriptive mathematical language. It is thus not only self-descriptive in nature, where logic denotes the rules of cognition, reasoning, inference, it is self-cognitive as well. The terms SCSPL and hology are explained further below. To skip immediately to the explanations, just click on the above links. An act is a temporal process, and self-inclusion is a spatial relation. The act of self-inclusion is thus where time becomes space. For the set of all sets, there can be no more fundamental process. No matter what else happens in the evolving universe, it must be temporally embedded in this dualistic self-inclusion operation. In the CTMU, the self-inclusion process is known as conspansion and occurs at the distributed, Lorentz invariant conspansion rate c, a time-space conversion factor already familiar as the speed of light in vacuo. Conspansion consists of two alternative phases accounting for the wave and particle properties of matter and affording a logical explanation for accelerating cosmic expansion. When we imagine a dynamic self-including set, we think of a set growing larger and larger in order to engulf itself from without. But since there is no without relative to the real universe, external growth or reference is not an option, there can be no external set or external descriptor. Instead, self-inclusion and self-description must occur inwardly as the universe stratifies into a temporal sequence of states, each state topologically and computationally contained in the one preceding it, where the conventionally limited term computation is understood to refer to a more powerful SCSPL-based concept, proto-computation, involving spatio-temporal parallelism. On the present level of discourse, this inward self-inclusion is the conspansive basis of what we call space-time. Every object in space-time includes the entirety of space-time as a state transition syntax according to which its next state is created. This guarantees the mutual consistency of states and the overall unity of the dynamic entity, the real universe. And because the sole real interpretation of the set theoretic entity, the set of all sets, is the entire real universe, the associated foundational paradoxes are resolved in kind, by attributing mathematical structure like that of the universe to the pure, uninterpreted set theoretic version of the set of all sets. Concisely, resolving the set of all sets paradox requires that 1. An endomorphism or self-similarity mapping D, S, RIS be defined for the set of all sets S and its internal points R. 2. There exist two complementary senses of inclusion, one topological set D, S, and one predicative D, S, et S, that allow the set to descriptively include itself from within, i.e. from a state of topological self-inclusion, where ET denotes topological or set theoretic inclusion and ED denotes descriptive inclusion, for example the inclusion in a language of its reference, and 3. The input S of D be global and structural, while the output D, S, equal, R at S, be internal to S and play a syntactic role. In short, the set theoretic and cosmological embodiments of the self-inclusion paradox are resolved by properly relating the self-inclusive object to the descriptive syntax in terms of which it is necessarily expressed, thus affecting true self-containment. The universe, set of all sets, is that which topologically contains that which descriptively contains the universe, set of all sets. This characterizes a system that consistently perceives itself and develops its own structure from within via holology, a two-stage form of self-similarity roughly analogous to holography. Holology is a logico-cybernetic form of self-similarity in which the global structure of a self-contained, self-interactive system doubles as its distributed self-transductive syntax. It is justified by the obvious fact that in a self-contained system, no other structure is available for that purpose. The associated conspansive mapping D is called incoversion in the spatiotemporally inward direction and coinversion in the reverse, outward, D1, direction. Incoversion carries global structure inward as state recognition and state transformation syntax, while coinversion projects syntactic structure outward in such a way as to recognize existing structure and determine future states in conformance with it. Incoversion is associated with an operation called requantization, while coinversion is associated with a complementary operation called inner expansion. The alternation of these operations, often referred to as wave-particle duality, comprises the conspansion process. The principle of conspansive duality then says that what appears as cosmic expansion from an interior, local, viewpoint appears as material and temporal contraction from a global viewpoint. Because metric concepts like size and duration are undefined with respect to the universe as a whole, the space-time metric is defined strictly intrinsically, and the usual limit of cosmological regress, a point like cosmic singularity, becomes the closed space-time algebra already identified as SCSPL. Thus, the real universe is not a static set, but a dynamic process resolving the self-inclusion paradox. Equivalently, because any real explanation of reality is contained in reality itself, reality gives rise to a paradox unless regarded as an include-user self-mapping. This is why, for example, category theory is increasingly preferred to set theory as a means of addressing the foundations of mathematics. It centers on invariant relations or mappings between covariant or contravariant, dually related, objects rather than on static objects themselves. For similar reasons, a focus on the relative invariance of semantic processes is also well suited to the formulation of evolving theories in which the definitions of objects and sets are subject to change. Thus, we can speak of time and space as equivalent to cognition and information with respect to the invariant semantic relation processes, as in time processes space and cognition processes information. But when we define reality as a process, we must reformulate containment accordingly. Concisely, reality theory becomes a study of SCSPL autology naturally formulated in terms of mappings. This is done by adjoining to logic certain metalogical principles, formulated in terms of mappings, that enable reality to be described as an autological, self-descriptive, self-recognizing/self-processing system. The first such principle is MAP, acronymic for metaphysical autology principle. Let S be the real universe, and let T equal T, S, be its theoretical description or TOE. Map, designed to endow T and S with mathematical closure, simply states that T and S are closed with respect to all internally relevant operations, including recognition and description. In terms of mappings, this means that all inclusional or descriptive mappings of S are automorphisms, for example, permutations or foldings, or endomorphisms, self-injections. Map is implied by the unlimited scope, up to perceptual relevance, of the universal quantifier implicitly attached to reality by the containment principle. With closure thereby established, we can apply techniques of logical reduction to S without worrying about whether the lack of some external necessity will spoil the reduction. In effect, map makes T, S, exclusive enough to describe S by excluding as a descriptor of S anything not in S. But there still remains the necessity of providing S with a mechanism of self-description. This mechanism is provided by another metalogical principle, the M=R or mind equals reality principle, that identifies S with the extended cognitive syntax D, S, of the theorist. This syntax, system of cognitive rules, not only determines the theorist's perception of the universe, but bounds his cognitive processes and is ultimately the limit of his theorization. This relates to the observation that all we can directly know of reality are our perceptions of it. The reasoning is simple. S determines the composition and behavior of objects, or subsystems, S in S, and thus comprises the general syntax, structural and functional rules of S, of which S obeys a specific restriction. Thus, where S is an ideal observer/theorist in S, S is the syntax of its own observation and explanation by S. This is directly analogous to the real universe contains all and only that which is real, but differently stated, S contains all and only objects S whose extended syntax is isomorphic to S. M=R identifies S with the veridical limit of any partial theory T of S lim T, S, equal D, S, thus making S inclusive enough to describe itself. That is, nothing relevant to S is excluded from S at D, S. Mathematically, the M=R principle is expressed as follows. The universe obviously has a structure S. According to the logic outlined above, this structure is self-similar. S distributes over S, where distributes over S means exists without constraint on location or scale within S. In other words, the universe is a perfectly self-similar system whose overall structure is replicated everywhere within it as a general state recognition and state transition syntax, as understood in an extended computational sense. The self-distribution of S, called hology, follows from the containment principle, i.e. the tautological fact that everything within the real universe must be described by the predicate real and thus fall within the constraints of global structure. That this structure is completely self-distributed implies that it is locally indistinguishable for subsystems S, it could only be discerned against its absence, and it is nowhere absent in S. Space-time is thus transparent from within, its syntactic structure invisible to its contents on the classical, macroscopic, level. Localized systems generally express and utilize only a part of this syntax on any given scale, as determined by their specific structures. I.e., where there exists a hological incoversion endomorphism D, SARIS carrying the whole structure of S into every internal point and region of S, objects, quantum geometrodynamically, embedded in S take their recognition and state transformation syntaxes directly from the ambient spatiotemporal background up to isomorphism. Objects thus utilize only those aspects of D, S, of which they are structural and functional representations. The inverse D1 of this map, Coin version, describes how an arbitrary local system S within S recognizes S at the object level and obeys the appropriate laws, ultimately giving rise to human perception. This reflects the fact that S is a self-perceptual system, with various levels of self-perception emerging within interactive subsystems S, where perception is just a refined form of interaction based on recognition in an extended computational sense. Thus, with respect to any class S of subsystems of S, we can define a homomorphic submap D of the endomorphism D, D, SAS expressing only that part of D to which S is isomorphic. In general, the SI are coherent or physically self-interactive systems exhibiting dynamical and informational closure. They have sometimes inaccessible internal structures and dynamics, particularly on the quantum scale, and are distinguishable from each other by means of informational boundaries contained in syntax and comprising a space-time metric. According to the above definitions, the global self-perceptor S is amenable to a theological interpretation, and its contents as to generalized cognitors including subatomic particles, sentient organisms, and every material system in between. Unfortunately, above the object level, the validity of S cognition, the internal processing of sentient subsystems S, depends on the specific cognitive functionability of a given S, the extent to which S can implicitly represent higher-order relations of S. In general relativity, S is regarded as given and complete, the laws of mathematics and science are taken as pre-existing. On the quantum scale, on the other hand, laws governing the states and distributions of matter and energy do not always have sufficient powers of restriction to fully determine quantum behavior, requiring probabilistic augmentation in the course of quantum wave function collapse. This prevents a given S, indeed anything other than S, from enclosing a complete nomology, set of laws, while a complete set of laws would amount to a complete deterministic history of the universe. Calling the universe completely deterministic amounts to asserting the existence of prior determinative constraints. But this is a logical absurdity, since if these constraints were real, they would be included in reality rather than prior or external to it, by the containment principle. It follows that the universe freely determines its own constraints, the establishment of nomology and the creation of its physical, observable, content being effectively simultaneous and recursive. The incoercive distribution of this relationship is the basis of free will, by virtue of which the universe is freely created by sentient agents existing within it. Let's elaborate a bit. Consider the universe as a completely evolved perceptual system, including all of the perceptions that will ultimately comprise it. We cannot know all of those perceptions specifically, but to the extent that they are interactively connected, we can refer to them en masse. The set of laws obeyed by the universe is just a minimal set of logical relations that suffices to make these perceptions non-contradictory, i.e. mutually consistent, and a distributed set of laws is just a set of laws formulated in such a way that the formulation can be read by any part of the system S. Obviously, for perceptions to be connected by laws, the laws themselves must be internally connected according to a syntax, and the ultimate syntax of nomological connectedness must be globally valid. Whatever the laws may be at any stage of system evolution, all parts of S must be able to unambiguously read them, execute and be acted upon by them, and recognize and be recognized as their reference. Unambiguously implies that two-valued logic is a primary ingredient of nomology. Its involvement is described by a third metalogical principle designed to ensure consistency, namely mu, or multiplex unity. This implies that the action and content of the laws are merged together in each part of the system as a single, but dual aspect, quantity, infocognition. The connectedness and consistency of infocognition is maintained by refinement and homogenization as nomological languages are superseded by extensional metalanguages in order to create and/or explain new data, because the theory SCSPL model theoretically equates itself to the real universe. Its creation and causal explanation operations are to a certain extent identical, and the SCSPL universe can be considered to create or configure itself by means of self-theorization or self-explanation. The simplest way to explain connected in this context is that every part of the object-level system relates to other parts within an overall structural description of the system itself. To interpret parts, think of events rather than objects. Objects are in a sense defined on events in a spatio-temporal setting. Obviously, any part which fails to meet this criterion does not conform to a description of the system and thus is not included in it, i.e. not connected to the system. On the other hand, if we were to insist that it is included or connected, then we would have to modify the systemic description accordingly. For this description to be util, it should be maximally compact, employing compact predictive generalizations in a regular way appropriate to structural categories, for example, employing general laws of physics. Because such laws, when formulated in an if conditions, A, B, C, exist, then, X and Y or Z, applies way, encode the structure of the entire system and are universally applicable within it, the system is self-distributed. In other words, Every part of the system can consistently interact with every other part while maintaining an integral identity according to this, formulation. Spatiotemporal relations can be skeletally depicted as edges in a graph whose vertices are events, physical interactions, i.e. space-time points. In this sense, graph-theoretic connectivity applies. But all those object-level connections must themselves be connected by more basic connections, the basic connections must be connected by even more basic connections, and so on. Eventually, perhaps sooner than later, we reach a basic level of connectivity whose syntax comprises a, partially undecidable, ultimate nomology for the level of reality we're discussing. Is this nomology, and the cognitive syntax in which it is expressed, wholly embodied by matter? In one sense the answer is yes, because S is distributed over each and every material cis as the reality syntax D, S. Thus, every axiom and theorem of mathematics can be considered implicit in material syntax and potentially exemplified by an appropriate material pattern, for example firing of cerebral neurons. Against holism, the idea that the universe is more than the sum of its parts, one can further object that the holistic entity in question is still a material ensemble, thus insinuating that even if the universe is not the sum of its parts, it is still a determinate function of its parts. However, this fails to explain the mutual consistency of object syntaxes, without the enforcement of which reality would disintegrate due to perceptual inconsistency. This enforcement function takes matter as its argument and must therefore be reposed in space-time itself, the universal substrate in which matter is unconditionally embedded, and as a geometrodynamic or quantum mechanical excitation of which matter is explained. So the background has logical ascendancy over derivative matter, and this permits it to have aspects, like the power to enforce consistency, not expressible by localized interactions of compact material objects, i.e., within the bounds of materialism as invoked regarding a putative lack of material evidence for God, excluding the entire material universe. On the other hand, might cognitive syntax reside in an external ideal realm analogous to Plato's world of Parmenidean forms? Plato's ideal abstract reality is explicitly set apart from actual concrete reality, the former being an eternal world of pure form and light, and the latter consisting of a cave on whose dirty walls shift murky, contaminated shadows of the ideal world above. However, if they are both separate and in mutual correspondence, these two realities both occupy a more basic joint reality enforcing the correspondence and providing the metric of separation. If this more basic reality is then juxtaposed to another, then there must be a more basic reality still, and so on until finally we reach the most basic level of all. At this level, there will, by definition, be no separation between the abstract and concrete phases, because there will be no more basic reality to provide it or enforce a remote correspondence across it. This is the inevitable logical terminus of Plato's regress. But it is also the reality specified by the containment principle, the scope of whose universal quantifier is unlimited up to perceptual relevance. Since it is absurd to adopt a hypothesis whose natural logical extension is a negation of that hypothesis, we must assume that the ideal plane coincides with this one, but again, not in a way necessarily accessible to identifiable physical operations. Rather, physical reality is embedded in a more general or abstract ideal reality equating to the reality syntax D, S, and the syntax D, S, is in turn embedded in physical reality by incoversion. Thus, if D, S, contains supraphysical components, they are embedded in S right along with their physical counterparts. Indeed, this convention is already in restricted use in string theory and M theory, where unseen higher dimensions get rolled up to sub-Planck diameter. What does this say about God? First, if God is real, then God inheres in the comprehensive reality syntax, and this syntax inheres in matter. Ergo, God inheres in matter, and indeed in its space-time substrate as defined on material and supramaterial levels. This amounts to pantheism, the thesis that God is omnipresent with respect to the material universe. Now, if the universe were pluralistic or reducible to its parts, this would make God, who coincides with the universe itself, a pluralistic entity with no internal cohesion. But because the mutual syntactic consistency of parts is enforced by a unitary holistic manifold with logical ascendancy over the parts themselves, because the universe is a dual-aspect monic entity consisting of essentially homogeneous, self-consistent infocognition, God retains monotheistic unity despite being distributed over reality at large. Thus, we have a new kind of theology that might be called monopantheism, or even more descriptively, holopantheism. Second, God is indeed real, for a coherent entity identified with a self-perceptual universe is self-perceptual in nature, and this endows it with various levels of self-awareness and sentience, or constructive, creative intelligence. Indeed, without a guiding entity whose self-awareness equates to the coherence of self-perceptual space-time, a self-perceptual universe could not coherently self-configure. Holopantheism is the logical, metatheological umbrella beneath which the great religions of mankind are unknowingly situated. Why, if there exists a spiritual metalanguage in which to establish the brotherhood of man through the unity of sentience, are men perpetually at each other's throats? Unfortunately, most human brains, which comprise a particular highly evolved subset of the set of all reality subsystems, do not fire in strict isomorphism much above the object level. Where we define one aspect of intelligence as the amount of global structure functionally represented by a given cis, brains of low intelligence are generally out of accord with the global syntax D, S. This limits their capacity to form true representations of S, global reality, by syntactic autology D, S, ed D, S, and make rational ethical calculations. In this sense, the vast majority of men are not well enough equipped, conceptually speaking, to form perfectly rational worldviews and societies. They are deficient in education and intellect, albeit remediably so in most cases. This is why force has ruled in the world of man, why might has always made right, despite its marked tendency to violate the optimization of global utility derived by summing over the sentient agents of S with respect to space and time. Now, in the course of employing deadly force to rule their fellows, the very worst element of humanity, the butchers, the violators, i.e. those of whom some modern leaders and politicians are merely slightly chastened copies, began to consider ways of maintaining power. They lit on religion, an authoritarian priesthood of which can be used to set the minds and actions of a populace for or against any given aspect of the political status quo. Others, jealous of the power thereby consolidated, began to use religion to gather their own sheep, promising special entitlements to those who would join them, mutually conflicting promises, now setting the promises at each other's throats. But although religion has often been employed for evil by cynics appreciative of its power, several things bear notice. 1. The abuse of religion, and the God concept, has always been driven by human politics, and no one is justified in blaming the God concept, whether or not they hold it to be real, for the abuses committed by evil men in its name. Abusus non tollit usum. 2. A religion must provide at least emotional utility for its believers, and any religion that stands the test of time has obviously been doing so. 3. A credible religion must contain elements of truth and undecidability, but no elements that are verifiably false, for that could be used to overthrow the religion and its sponsors. So by design, religious beliefs generally cannot be refuted by rational or empirical means. Does the reverse apply? Can a denial of God be refuted by rational or empirical means? The short answer is yes. The refutation follows the reasoning outlined above. That is, the above reasoning constitutes not just a logical framework for reality theory, but the outline of a logical proof of God's existence and the basis of a logical theology. While the framework serves other useful purposes as well, for example the analysis of mind and consciousness, we'll save those for another time. Physics and Metaphysics. At a January 1998 meeting of the American Astronomical Society, it was announced that a survey of distant supernovae by an international team of astronomers indicates that cosmic expansion is being accelerated by an unknown repulsive force, a force that appears strong enough to prevent gravity from collapsing the universe. The supernovae are of an extensively studied variety known as Type Ia. Type Ia supernovae, which result from the explosion of certain white dwarf stars, are so similar and steady in luminosity that they can be used as standard candles, or reliable measures of astral brightness. Because they always shine with the same intrinsic intensity, it is possible to infer their distances by the dimness of their light. Distance can then be plotted against speed of recession as calculated from frequency reductions due to cosmic redshift. Such a plot turns out to be increasingly nonlinear as distance increases, suggesting an unexpected acceleration. Most of those analyzing the data agree on the implications. Because the observed supernovae are dimmer than would be expected had the rate of cosmic expansion remained constant since their parent stars exploded, expansion must have accelerated since the supernovae were born, and some kind of accelerative force must pervade the universe. As early as February 1998, an independent group calling itself the High Z Supernova Search Team, Z means redshift, confirmed this finding with a statistical confidence of 98.7 to 99.99%. Since then, further observations have provided yet more confirmation. Among the candidates for a repulsive force are Einstein's cosmological constant, representing a form of anti-gravity associated with general relativity, and quantum mechanical vacuum energy, which produces outward pressure through the spontaneous creation and annihilation of virtual particle-antiparticle pairs. Also receiving welcome airtime are more bizarre ideas like X-matter and quintessence, strange forms of background energy that might be produced by mysterious physical processes as yet unidentified. In the minds of most theorists, the best bet is a combination of cosmological constant and vacuum energy. That would deliver the steady effect that has been observed, as opposed to the fluctuations that might accompany X-matter and quintessence. Unfortunately, none of the experts can give a constructive reason for why any of these influences should themselves exist. No conventional theory incorporating the standard Big Bang model of cosmology can explain why an expansive force should be evident or how it might have originated. However, an alternative theory does exist. It is virtually unknown to most physicists, whose stock repertoire is limited to theories that have been published by other physicists in exclusive scholastic journals unreceptive to strange new ideas emanating from unknown, academically uncredentialed sources. It has, however, been published for a highly intelligent readership in a journal called Noesis. This theory is called the CTMU. Although Noesis is not, strictly speaking, a peer-reviewed journal, the CTMU has been extensively criticized and defended within it over the last decade on the basis of published descriptions. The CTMU is not an ordinary physical theory. Instead of being just another system of ad hoc equations purporting to describe some limited aspect of the physical universe, it has a unique logical structure designed to embed the very foundations of mathematics and philosophy. Yet, unlike many predominantly rationalistic theories, it is designed to resolve paradox on both rational and observational levels, and thus makes verifiable statements regarding the nature of observable reality. Some of these statements, which range in application from quantum physics to cosmology, relate to cosmic expansion. To query the universe regarding its true nature is to ask a very deep question. There was always a strange and touching mixture of humility and hubris in the idea that physicists could obtain an answer to this question simply by looking through their instruments and carefully describing what they saw. After all, reality contains features like mind, cognition, and consciousness that do not lend themselves to empirical techniques or scientific reductionism. Yet, they are basic, unavoidable ingredients of every scientific measurement ever performed and every theoretical explanation ever devised. Without conscious minds subjecting reality to cognition, science could not exist. The CTMU provides physics and cosmology with a logical framework that incorporates these missing ingredients in a way reflecting the nature of their involvement in measurement and theorization. And as a bonus, it does what no other theory can, while painlessly absorbing the bulk of modern physical science and resolving many of its most stubborn and destructive paradoxes. It coherently explains the cosmological implications of the evidence for accelerative recession of type Ia supernovae in the context of a self-contained, self-creating universe. Physics and Metaphysics, copyright 1998-2002 by C. M. Langen. Today, metaphysics, tomorrow, physics. Today's dominant theory of small-scale physics, quantum mechanics, did not begin its long and successful run as a physical theory. The reason is logical. Its major premise, the Heisenberg uncertainty principle, sets absolute limits on the accuracy to which quanta can be measured, and cursory logical analysis reveals that this defines a relation between measurer and measured object that cannot be expressed in a language describing measured objects alone. Since classical physics was the latter kind of language, neither the uncertainty principle nor quantum mechanics could be immediately classified as physics. Rather, they belonged to a logical meta-language of physics called metaphysics. Indeed, even at a time when physics routinely explains what the ancients would have seen as magic, some physicists view quantum mechanics with a touch of uneasy skepticism. The reason: it raises too many metaphysical-looking issues without satisfactorily resolving them. Relativity too was initially a metaphysical theory based on the formation of higher-order predicates, space-time and space-time curvature, that had not existed in physics, drawing in the interests of self-containment a higher-order causal relationship between the fundamental physical parameters space, time, and matter on a combination of empirical and mathematical grounds. A higher-order relation is a relation of relations of primitive objects, defined at the appropriate level of predicate logic. Since this describes a semantic operation that cannot be effected within the bare language of physics as it existed at the time, relativity was metaphysical rather than physical in nature. Nevertheless, it achieved quick recognition as a physical theory not only because Einstein was already recognized as a professional physicist, but because it made physical predictions that classical physics alone did not make. It was recognized long before Einstein that observations of physical objects vary subjectively in certain parameters. For example, although objects are identical when viewed under identical conditions, they vary in size when viewed from different distances, display different shapes from different angles, and seem to be differently colored and shaded under different lighting conditions. Einstein expanded the range of subjective variation of physical phenomena by showing that objects also look different when viewed at different relative velocities. But in keeping with classical objectivism, he showed in the process that such perceptual variations were a matter of objective circumstance, in effect treating perception itself as an objective phenomenon. Because this kind of empirical objectivization is exactly what is expected of the objective empirical science of physics, attention was diverted from nagging metaphysical questions involving the interplay of rational and empirical factors in perception. Although he never got around to enunciating it, Einstein may well have sensed that perception cannot be understood without understanding the logic of this interplay, and that this logic is instrumental to the inherently metaphysical operation of theoretical unification. Nevertheless, perhaps encouraged by his own apparent success in sidestepping this particular metaphysical issue, he spent the second half of his career on a doomed attempt to unify physics in a purely physical context, that is, in the context of a space-time model which went only as far as relativity theory. Since then, many bright and well-educated people have repeated roughly the same error, never realizing that physical theory truly advances only by absorbing profoundly creative metaphysical extensions on which no ordinary physicist would wittingly sign off. Like quantum mechanics and the theory of relativity, the CTMU is a metaphysical theory that makes distinctive predictions and retrodictions not made by previous theories. However, the CTMU makes no attempt in the process to sidestep difficult metaphysical issues. For example, Einstein introduced the cosmological constant to stabilize the size of the universe, but then dropped it on the empirical grounds of apparent universal expansion. In contrast, the CTMU goes beyond empiricism to the rational machinery of perception itself, providing cosmic expansion with a logical basis while predicting and explaining some of its features. Relativity pursues the goal of explanatory self-containment up to a point. Space-time contains matter and energy that cause space-time fluctuations that cause changes in matter and energy. The CTMU, on the other hand, pursues the goal of self-containment all the way up to cosmogenesis. And while neither Gross nor QM does anything to resolve the fatal paradoxes of ex nihilo creation and quantum non-locality, the CTMU dissolves such paradoxes with a degree of logical rectitude to which science seldom aspires. To understand how the CTMU is a natural extension of modern physics, let us review the history of the physicists' and cosmologists' art in the context of Cartesian coordinate systems. The Cartesian architecture of split-level reality. Modern physics is based on, and can be described as the evolution of, rectilinear coordinate systems. Called Cartesian coordinate systems after their leading exponent, René Descartes, they are particularly well suited to the objective modeling of physical phenomena, that is, to the algebraic representation of static and dynamic relationships without respect to their locations or the special vantages from which they are observed or considered. This property of Cartesian spaces relates directly to another invention of Monsieur Descartes called mind-body dualism, which merely states in plain language what Cartesian coordinate systems seem to graphically depict, namely, that cognition and physical reality can be factored apart at our philosophical and scientific convenience. Since the time of Descartes, there have been numerous attempts to clarify the exact relationship between mind and reality and thereby solve the mind-body problem. Hume, for example, held that reality consists exclusively of sense impressions from which concepts like mind and matter are artificially abstracted. Kant countered with the view that the mind knows deep reality only through cryptic impressions molded to its own cognitive categories. More recently, Lewis' dual-aspect monism maintained that reality consists of a neutral substance of which mind and body are just complementary aspects, while the mind-stuff theory of Clifford and Prince was a form of psychical monism positing that mind is the ultimate reality, that ordinary material reality is simply mind apprehended by mind, and that the higher functions of mind emerge from smaller pieces of mind that do not of themselves possess higher mental attributes, an idea previously attributable to Leibniz, Spencer, and others. But while each of these theories contains a part of the truth, none contains the whole truth. Only recently have the parts been assembled in light of modern logic and science to create a dynamic, comprehensive theory of reality that solves the mind-body problem for good. Classical mechanics, the infinitesimal worm in Newton's apple. The next big representational advance in physics, Newtonian mechanics, relied on a new kind of analytic geometry based on vector modeling and vector analysis of physical motion in Cartesian coordinate systems in which space and time are represented as independent, orthogonal, axes. Its Lagrangian and Hamiltonian formulations occupy the same mathematical setting. From the beginning, the featureless neutrality of Cartesian space accorded well with the evident non-preference of physical laws for special coordinate systems, i.e., for the homogeneity and isotropy of space and time. However, this property of Cartesian spaces also rendered position and motion completely relative in the Galilean sense. Finding that this made it hard to explain certain physical phenomena, for example, inertia, and later on, electromagnetic wave propagation, Newton and his followers embraced the concept of a stationary ether against whose background all dimensions, durations, and velocities were considered to be fixed. The ether was an unusual kind of field over which the center of mass of the universe was perfectly distributed, explaining not only inertia but the evident fact that all of the matter in the universe was not gravitating toward a central point in space. In order to work with his vector model of physical reality, Newton had to invent a new kind of mathematical analysis known as infinitesimal calculus. Specifically, he was forced in calculating the velocity of an object at each point of its trajectory to define its instantaneous rate of change as a ratio of infinitesimal vectors whose lengths were smaller than any finite quantity, but greater than zero. Since this is a paradoxical description that does not meaningfully translate into an actual value, the only number usually considered to be smaller than any finite quantity is zero, it is hard to regard infinitesimal vectors as meaningful objects. But even though they could not give a satisfactory account of infinitesimal vectors, post-Newtonian physicists at least knew where such vectors were located, in the same Cartesian space containing ordinary finite vectors. Better yet, the celebrated mathematician Gauss discovered that they could be confined within the curves to which they were tangential, an insight developed by Riemann into a comprehensive theory of differential geometry valid for curved surfaces in any number of dimensions. However, although differential geometry would later prove useful in formulating a generalization of Cartesian space, its intrinsic nature did not resolve the paradox of infinitesimals. For many years after Newton, mathematicians struggled to find a way around the infinitesimals paradox, first lighting on the Weierstrass epsilon delta formalism purporting to characterize infinitesimals within standard Cartesian space. But later, in fact, years after Newtonian mechanics was superseded by a more general theory of physics, they finally satisfied their yearning to understand infinitesimals as timeless mathematical objects. They accomplished this by reposing them in a hypothetical non-standard universe where each point of the standard universe is surrounded by a non-standard neighborhood containing infinitesimal objects. In logic, a theory is justified by demonstrating the existence of a model for which it is true. As a model of infinitesimals and their relationships with finite numbers, the non-standard universe justifies the infinitesimal calculus. Ignoring the obvious fact that this could have a metaphysical bearing on physical reality, mathematicians took the non-standard universe and carried it off in the purely abstract direction of non-standard analysis. Quantum mechanics, space and time get smeared, and worse. After standing for over 2 centuries as the last word in physics, the differential equations comprising the deterministic laws of Newtonian mechanics began to run into problems. One of these problems was called the Heisenberg uncertainty principle, or HUP. The HUP has the effect of blurring space and time on very small scales by making it impossible to simultaneously measure with accuracy certain pairs of attributes of a particle of matter or packet of energy. Because of this blurring, Newton's differential equations are insufficient to describe small-scale interactions of matter and energy. Therefore, in order to adapt the equations of classical mechanics to the non-deterministic, dualistic, wave versus particle, nature of matter and energy, the more or less ad hoc theory of quantum mechanics, QM, was hastily developed. QM identifies matter quanta with probability waves existing in n-dimensional complex Hilbert space, a Cartesian space defined over the field of complex numbers a plus b, where a and b are real numbers and I equal 01, instead of the pure real numbers, and replaces Hamilton's classical equations of motion with Schrödinger's wave equation. QM spelled the beginning of the end for Laplacian determinism, a philosophical outgrowth of Newtonianism which held that any temporal state of the universe could be fully predicted from a complete Cartesian description of any other. Not only uncertainty but freedom had re-entered the physical arena. Unfortunately, the HUP was not the only quantum mechanical problem for classical physics and its offshoots. Even worse was a phenomenon called EPR, Einstein-Podolsky-Rosen, non-locality, according to which the conservation of certain physical quantities for pairs of correlated particles seems to require that information be instantaneously transmitted between them regardless of their distance from each other. The EPR paradox juxtaposes non-locality to the conventional dynamical scenario in which anything transmitted between locations must move through a finite sequence of intervening positions in space and time. So basic is this scenario to the classical worldview that EPR non-locality seems to hang over it like a Damocles sword, poised to sunder it like a melon. Not only does no standard physical theory incorporating common notions of realism, induction, and locality contain a resolution of this paradox, this much we know from a mathematical result called Bell's theorem, but it seems that the very foundations of physical science must give way before a resolution can even be attempted. The special theory of relativity, space and time beget space-time. Another problem for Newton's worldview was the invariance of c, the speed of light in vacuo. Emerging from Maxwell's equations and direct experimentation, for example, Michelson-Morley, c invariance defies representation in an ordinary Cartesian vector space. Einstein's special theory of relativity, SR, arising at about the same time as quantum mechanics, was designed to fill the breach. To accomplish this, Einstein had to generalize Cartesian space in such a way that distances and durations vary with respect to distinct coordinate systems associated with various states of relative motion. The particular generalization of Cartesian space in which these motion-dependent coordinate systems are related, and in which the velocity of light can be invariantly depicted, is called Minkowski space-time. In space-time, space and time axes remain perpendicular but no longer represent independent dimensions. Instead, space-like and time-like domains are separated by null or light-like geodesics, minimal trajectories, representing the paths traced by light, and the constant velocity of light is represented by the constant, usually 45 degrees, orientation of the corresponding space-time vectors. The space and time axes of moving coordinate systems are skewed by the Lorentz transformation functions according to their relative angles of propagation, velocities, through time-like domains, resulting in relative distortions of space and time vectors between systems. General relativity, space-time develops curvature. Flat or Euclidean space-time suffices for the representation of all kinds of physical motion up to constant linear acceleration. However, gravity, which Newton had regarded as a force and represented as an ordinary Cartesian vector, causes other kinds of motion as well, for example orbital motion. So in order to generalize Minkowski spacetime to explain gravity, Einstein had to undertake a further generalization of Cartesian space accommodating non-flat or curved spacetime. In this generalization of Cartesian space, space-time curvature is represented by algebraically well-behaved generalizations of vectors called tensors, which are just mathematical functions that take ordinary space-time vectors as input and yield other vectors, or numbers, as output. Calculating these entities can be as exacting and tedious as counting sand grains, but they are mathematically straightforward. By modeling physical reality as a curved tensor manifold, Einstein was able to explain how gravity affects motion and thus to create the gravitational extension of special relativity known as general relativity or Gross. While the gravitational calculations of Gross match those of classical mechanics under most conditions, experiment favors Gross decisively in certain situations. Although Gross is based on differential geometry intrinsic to curved surfaces, geometry in which one need never leave a surface in order to determine its properties, distances and curvatures are ultimately expressed in terms of minute spatiotemporal vectors or line elements, which must be made infinitesimal to ensure that they never leave the surface of space-time. Thus, Gross avoids the mensural necessity of an external hyperspace only by inheriting Newton's infinitesimals paradox. Since Gross, like classical mechanics, treats these line elements as objects to be used in forming ratios and tensors, it requires an object-oriented, as opposed to a Weierstrass-style procedural, definition of infinitesimals. But such a definition requires a non-standard universe on model-theoretic grounds. So Gross depends on a non-standard universe as much as its predecessors, and is not as self-contained as the concept of intrinsic curvature might lead one to expect. Strictly speaking, Newtonian mechanics and all subsequent theories of physics require a non-standard universe, i.e. a model that supports the existence of infinitesimals, for their formulation. The effect of this requirement is to blur the distinction between physics, which purports to limit itself to the standard universe of measurable distances, and metaphysics, which can describe the standard universe as embedded in a higher dimensional space or a non-standard universe containing infinitesimals. The fast acceptance of Gross as a physical theory thus owed at least in part to the fact that physicists had already learned to swallow the infinitesimals paradox every time they used the infinitesimal calculus to do classical mechanics. Only much later, with the advent of an infocognitive spacetime internally accommodating necessary metaphysical self-extensions, could the infinitesimal line elements of Gross be properly embedded in a neo-Cartesian model of reality as abstract ingredients of certain distributed computations, see Appendix A. The moral of the story up to this point is abundantly clear: both before and after Newton, the greatest advances in physics have come through the creation and absorption of metaphysical extensions. Unfortunately, most physicists are sufficiently unclear on this fact that the word metaphysics remains all but unmentionable in their deliberations. But change finds a way. The search for a unified field, space-time, gains new dimensions. Having found so satisfying a mathematical setting for gravitation, Einstein next tried to create a unified field theory, UFT, by using the same model to explain all of the fundamental forces of nature, two of which, electricity and magnetism, had already been unified by Maxwell as electromagnetism, or M for short. As a natural first step, Einstein tried to formulate the M-force as a tensor. Unfortunately, M-force is governed by quantum mechanics, and four-dimensional Gross tensors lack intrinsic quantum properties. This alone limits general relativity to a calculational rather than explanatory bearing on electromagnetism. Because the branch of quantum mechanics called quantum electrodynamics, QED, which treats the M-force as a particle interchange, better explained the properties and dynamics of electrons and electromagnetic fields, Einstein's geometrodynamic approach to the UFT was widely abandoned. After a time, however, the trek was resumed. Kaluza-Klein theory had already added an extra dimension to space-time and curled it up into a tight little loop of radius equal to the Planck length, 10 to 33 centimeters, far smaller than any known particle. This curling maneuver explained more than the extra dimension's invisibility, because only a discrete number of waves can fit around a loop. It also seemed to explain why particle energies are quantized, and thus to provide a connection between relativity theory and QM. In 1921, Kaluza observed that light could be viewed as the product of fifth-dimensional vibrations. Though temporarily forgotten, this idea was ultimately revived in connection with supersymmetry, an attempt to unify the fundamental forces of nature in a single theory by defining Gross-style tensors accommodating 7 additional space-time dimensions. Shortened and rolled up in bizarre topological configurations, these dimensions would exhibit fundamental frequencies and quantized harmonics resembling the quantum properties of tiny particles of matter. Although supersymmetry was eventually dropped because its 11-dimensional structure failed to explain subatomic chirality, whereby nature distinguishes between right and left-handedness, its basic premises lived on in the form of 10-dimensional superstring theory. Again, the basic idea was to add additional dimensions to gross, slice, and splice these extra dimensions in such a way that they manifest the basic features of quantum mechanics, and develop the implications in the context of a series of Big Bang phase transitions, broken symmetries, in which matter changes form as the hot early universe cools down. Mathematically, these phase transitions are represented by the arrows in the series Gaha Asu, 3, Xu, 2, Xu, 1, Asu, 3, Xu, 1, where alphanumerics represent algebraic symmetry groups describing the behavioral regularities of different kinds of matter under the influence of different forces, and gravity is mysteriously missing. Unfortunately, just as general relativity did nothing to explain the origin of 4D spacetime or its evident propensity to expand when there would seem to be nothing for it to expand into, string theory did nothing to explain the origin or meaning of the n-dimensional strings into which spacetime had evolved. Nor did it even uniquely or manageably characterize higher-dimensional spacetime structure. It required the same kind of non-standard universe that was missing from Gross in order to properly formulate quantum-scale dimensional curling, and eventually broke down into 5 incompatible versions, all relying on difficult and ill-connected kinds of mathematics that made even the simplest calculations, and extracting even the most basic physical predictions, virtually impossible. Worse yet, it was an unstratified low-order theory too weak to accommodate an explanation for quantum non-locality or measurable cosmic expansion. Recently, string theory has been absorbed by a jury-rigged patchwork called membrane theory or M-theory, whose basic entity is a p-dimensional object called, one might almost suspect eponymically, a p-brane. No, this is not a joke. P-branes display mathematical properties called S and T duality, which combine in a yet higher level duality called the duality of dualities. Again, this is not a joke, that suggests a reciprocity between particle size and energy that could eventually link the largest and smallest scales of the universe, and thus realize the dream of uniting large-scale physics, gross, with small-scale physics, QM. In some respects, this is a promising insight. It applies broad logical properties of theories, for example, duality, to what the theories objectively describe, thus linking reality in a deeper way to the mental process of theorization. At the same time, the membranes or bubbles that replace strings in this theory more readily lend themselves to certain constructive interpretations. But in other ways, M-theory is just the same old lemon with a new coat of paint. Whether the basic objects of such theories are called strings, p-branes, or bubble branes, they lack sufficient structure and context to explain their own origins or cosmological implications, and are utterly helpless to resolve physical and cosmological paradoxes like quantum non-locality and ex nihilo, something from nothing, cosmogony paradoxes, next to which the paradoxes of broken symmetry resolved by such theories resemble the unsightly warts on the nose of a charging rhinoceros. In short, such entities sometimes tend to look to those unschooled in their virtues like mathematical physics run wildly and expensively amok. Alas, the truth is somewhat worse. Although physics has reached the point at which it can no longer credibly deny the importance of metaphysical criteria, it resists further metaphysical extension. Instead of acknowledging and dealing straightforwardly with its metaphysical dimension, it mislabels metaphysical issues as scientific issues and festoons them with increasingly arcane kinds of mathematics that hide its confusion regarding the underlying logic. Like a social climber determined to conceal her bohemian roots, it pretends that it is still dealing directly with observable reality instead of brachioteing up vertiginous rationalistic tightropes towards abstractions that, while sometimes indirectly confirmed, are no more directly observable than fairies and unicorns. And as science willfully distracts itself from the urgent metaphysical questions it most needs to answer, philosophy ignores its parental responsibility. Reality as a cellular automaton, space-time trades curves for computation. At the dawn of the computer era, the scientific mainstream sprouted a timely alternative viewpoint in the form of the cellular automaton model of the universe, which we hereby abbreviate as the CAMU. First suggested by mathematician John von Neumann and later resurrected by salesman and computer scientist Ed Fredkin, the CAMU represents a conceptual regression of space-time in which space and time are re-separated and described in the context of a cellular automaton. Concisely, space is represented by, for example, a rectilinear array of computational cells, and time by a perfectly distributed state transformation rule uniformly governing cellular behavior. Because automata and computational procedures are inherently quantized, this leads to a natural quantization of space and time. Yet another apparent benefit of the CAMU is that if it can be made equivalent to a universal computer, then by definition it can realistically simulate anything that a consistent and continually evolving physical theory might call for, at least on the scale of its own universality. But the CAMU, which many complexity theorists and their sympathizers in the physics community have taken quite seriously, places problematic constraints on universality. For example, it is not universal on all computational scales, does not allow for subjective cognition except as an emergent property of its, assumedly objective, dynamic, and turns out to be an unmitigated failure when it comes to accounting for relativistic phenomena. Moreover, it cannot account for the origin of its own cellular array and is therefore severely handicapped from the standpoint of cosmology, which seeks to explain not only the composition but the origin of the universe. Although the CAMU array can internally accommodate the simulations of many physical observables, thus allowing the CAMU's proponents to intriguingly describe the universe as a self-simulation, its inability to simulate the array itself precludes the adequate representation of higher-order physical predicates with a self-referential dimension. Reality as reality theory, space-time turns introspective. Now let us backtrack to the first part of this history, the part in which René Descartes physically objectivized Cartesian spaces in keeping with his thesis of mind-body dualism. Notice that all of the above models sustain the mind-body distinction to the extent that cognition is regarded as an incidental side effect or irrelevant epiphenomenon of objective laws. Cognition is secondary even where space and time are considered non-independent. Yet not only is any theory meaningless in the absence of cognition, but the all-important theories of relativity and quantum mechanics, without benefit of explicit logical justification, both invoke higher-level constraints which determine the form or content of dynamical entities according to properties not of their own, but of entities that measure or interact with them. Because these higher-level constraints are cognitive in a generalized sense, Gross and QM require a joint theoretical framework in which generalized cognition is a distributed feature of reality. Let's try to see this another way. In the standard objectivist view, the universe gives rise to a theorist who gives rise to a theory of the universe. Thus, while the universe creates the theory by way of a theorist, it is not beholden to the possibly mistaken theory that results. But while this is true as far as it goes, it cannot account for how the universe itself is created. To fill this gap, the CTMU metaphysical autology principle or map states that because reality is an all-inclusive relation bound by a universal quantifier whose scope is unlimited up to relevance, there is nothing external to reality with sufficient relevance to have formed it, hence, the real universe must be self-configuring. And the mind equals reality, M equal R, principle says that because the universe alone can provide the plan or syntax of its own self-creation, it is an infocognitive entity loosely analogous to a theorist in the process of introspective analysis. Unfortunately, Since objectivist theories contain no room for these basic aspects of reality, they lack the expressive power to fully satisfy relativistic, cosmological, or quantum mechanical criteria. The ubiquity of this shortcoming reflects the absence of a necessary and fundamental logical feature of physical analysis, a higher order of theorization in which theory cognitively distributes over theory, for which no conventional theory satisfactorily accounts. In view of the vicious paradoxes to which this failing has led, it is only natural to ask whether there exists a generalization of space-time that contains the missing self-referential dimension of physics. The answer, of course, is that one must exist, and any generalization that is comprehensive in an explanatory sense must explain why. In Noesis/ES 139, the SCSPL paradigm of the CTMU was described to just this level of detail. Space and time were respectively identified as generalizations of information and cognition, and space-time was described as a homogeneous self-referential medium called infocognition that evolves in a process called conspansion. Conspansive spacetime is defined to incorporate the fundamental concepts of Gross and QM in a simple and direct way that effectively preempts the paradoxes left unresolved by either theory alone. Conspansive spacetime not only incorporates non-independent space and time axes, but logically absorbs the cognitive processes of the theorist regarding it. Since this includes any kind of theorist cognitively addressing any aspect of reality, scientific or otherwise, the CTMU offers an additional benefit of great promise to scientists and non-scientists alike. It naturally conduces to a unification of scientific and non-scientific, for example humanistic, artistic, and religious, thought. CTMU Camus in Camo. Before we explore the conspansive SCSPL model in more detail, it is worthwhile to note that the CTMU can be regarded as a generalization of the major computation theoretic current in physics, the Camus. Originally called the computation theoretic model of the universe, the CTMU was initially defined on a hierarchical nesting of universal computers, the nested simulation tableau or NEST, which tentatively described spacetime as stratified virtual reality in order to resolve a decision-theoretic paradox put forth by Los Alamos physicist William Newcomb, see Noesis 44, etc. Newcomb's paradox is essentially a paradox of reverse causality with strong implications for the existence of free will, and thus has deep ramifications regarding the nature of time in self-configuring or self-creating systems of the kind that MAP shows it must be. Concisely, it permits reality to freely create itself from within by using its own structure, without benefit of any outside agency residing in any external domain. Although the CTMU subjects NEST to metalogical constraints not discussed in connection with Newcomb's paradox, NEST-style computational stratification is essential to the structure of conspansive spacetime. The CTMU thus absorbs the greatest strengths of the Camus, those attending quantized distributed computation without absorbing its a priori constraints on scale or sacrificing the invaluable legacy of relativity. That is, because the extended CTMU definition of spacetime incorporates a self-referential, self-distributed, self-scaling universal automaton, the tensors of Gross and its many-dimensional offshoots can exist within its computational matrix. An important detail must be noted regarding the distinction between the Camus and CTMU. By its nature, the CTMU replaces ordinary mechanical computation with what might better be called proto-computation. Whereas computation is a process defined with respect to a specific machine model, for example a Turing machine, proto-computation is logically pre-mechanical. That is, before computation can occur, there must, in principle, be a physically realizable machine to host it. But in discussing the origins of the physical universe, the prior existence of a physical machine cannot be assumed. Instead, we must consider a process capable of giving rise to physical reality itself, a process capable of not only implementing a computational syntax, but of serving as its own computational syntax by self-filtration from a realm of syntactic potential. When the word computation appears in the CTMU, it is usually to proto-computation that reference is being made. It is at this point that the theory of languages becomes indispensable. In the theory of computation, a language is anything fed to and processed by a computer, thus, if we imagine that reality is in certain respects like a computer simulation, it is a language. But where no computer exists, because there is not yet a universe in which it can exist, there is no hardware to process the language, or for that matter the metalanguage simulating the creation of hardware and language themselves. So with respect to the origin of the universe, language and hardware must somehow emerge as one. Instead of engaging in a chicken or egg regress involving their recursive relationship, we must consider a self-contained, dual-aspect entity functioning simultaneously as both. By definition, this entity is a self-configuring self-processing language or SCSPL. Whereas ordinary computation involves a language, proto-computation involves SCSPL. Proto-computation has a projective character consistent with the SCSPL paradigm. Just as all possible formations in a language, the set of all possible strings, can be generated from a single distributed syntax, and all grammatical transformations of a given string can be generated from a single copy thereof, all predicates involving a common syntactic component are generated from the integral component itself. Rather than saying that the common component is distributed over many values of some differential predicate, for example, that some distributed feature of programming is distributed over many processors, we can say, to some extent equivalently, that many values of the differential predicate, for example spatial location, are internally or endomorphically projected within the common component, with respect to which they are in superposition. After all, difference or multiplicity is a logical relation, and logical relations possess logical coherence or unity, where the relation has logical priority over the realand, unity has priority over multiplicity. So instead of putting multiplicity before unity and pluralism ahead of monism, CTMU proto-computation, under the mandate of a third CTMU principle called multiplex unity or mu, puts the horse sensibly ahead of the cart. To return to one of the central themes of this article, SCSPL and proto-computation are metaphysical concepts. Physics is unnecessary to explain them, but they are necessary to explain physics. So again, what we are describing here is a metaphysical extension of the language of physics. Without such an extension linking the physical universe to the ontological substrate from which it springs, explaining what physical reality is, where it came from, and how and why it exists, the explanatory regress of physical science would ultimately lead to the inexplicable and thus to the meaningless. Space-time requantization and the cosmological constant. The CTMU, and to a lesser extent Gross itself, posits certain limitations on exterior measurement. Gross utilizes, so-called, intrinsic space-time curvature in order to avoid the necessity of explaining an external metaphysical domain from which space-time can be measured, while Map simply states, in a more sophisticated way consistent with infocognitive space-time structure as prescribed by M=R and mu, that this is a matter of logical necessity, see Noesis/ES 139, pages 3-10. Concisely, if there were such an exterior domain, then it would be an autologous extrapolation of the human cognitive syntax, HCS, that should properly be included in the space-time to be measured. As previously explained, the HCS, a synopsis of the most general theoretical language available to the human mind, cognition, is a supertautological formulation of reality as recognized by the HCS. Where CTMU spacetime consists of HCS infocognition distributed over itself in a way isomorphic to Nest, i.e., of a stratified Nest computer whose levels have infocognitive HCS structure, the HCS spans the laws of mind and nature. If something cannot be mapped to HCS categories by acts of cognition, perception, or reference, then it is HCS unrecognizable and excluded from HCS reality due to non-homomorphism. Conversely, if it can be mapped to the HCS in a physically relevant way, then it is real and must be explained by reality theory. Accordingly, the universe as a whole must be treated as a static domain whose self and contents cannot expand, but only seem to expand because they are undergoing internal rescaling as a function of SCSPL grammar. The universe is not actually expanding in any absolute, externally measurable sense, rather, its contents are shrinking relative to it, and to maintain local geometric and dynamical consistency, it appears to expand relative to them. Already introduced as conspansion, contraction qua expansion, this process reduces physical change to a form of grammatical substitution in which the geometrodynamic state of a spatial relation is differentially expressed within an ambient cognitive image of its previous state. By running this scenario backwards and regressing through time, we eventually arrive at the source of geometrodynamic and quantum theoretic reality, a primeval conspansive domain consisting of pure physical potential embodied in the self-distributed infocognitive syntax of the physical universe, i.e., the laws of physics, which in turn reside in the more general HCS. Conspansion consists of two complementary processes, requantization and inner expansion. Requantization downsizes the content of Planck's constant by applying a quantized scaling factor to successive layers of space corresponding to levels of distributed parallel computation. This inverse scaling factor 1/r is just the reciprocal of the cosmological scaling factor r, the ratio of the current apparent size dn, u, of the expanding universe to its original, Higgs condensation, size d0, u, equal 1. Meanwhile, inner expansion outwardly distributes the images of past events at the speed of light within progressively requantized layers. As layers are rescaled, the rate of inner expansion, and the speed and wavelength of light, change with respect to d0, u, so that relationships among basic physical processes do not change, i.e., so as to affect nomological covariance. The thrust is to relativize space and time measurements so that spatial relations have different diameters and rates of diametric change from different space-time vantages. This merely continues a long tradition in physics, just as Galileo relativized motion and Einstein relativized distances and durations to explain gravity. This is a relativization for conspansive antigravity, see Appendix B. Conspansion is not just a physical operation, but a logical one as well. Because physical objects unambiguously maintain their identities and physical properties as space-time evolves, space-time must directly obey the rules of 2VL, two-valued logic distinguishing what is true from what is false. Space-time evolution can thus be straightforwardly depicted by Venn diagrams in which the truth attribute, a high-order meta-predicate of any physical predicate, corresponds to topological inclusion in a spatial domain corresponding to specific physical attributes. I.e., to be true, an effect must be not only logically but topologically contained by the cause, to inherit properties determined by an antecedent event. Objects involved in consequent events must appear within its logical and spatio-temporal image. In short, logic equals space-time topology. This 2VL rule, which governs the relationship between the space-time object and logico-mathematical subsyntaxes of the HCS, follows from the dual relationship between set theory and semantics, whereby predicating membership in a set corresponds to attributing a property defined on or defining the set. The property is a qualitative space topologically containing that to which it is logically attributed. Since the laws of nature could not apply if the sets that contain their arguments and the properties that serve as their parameters were not mutually present at the place and time of application, and since QM blurs the point of application into a region of distributive space-time potential, events governed by natural laws must occur within a region of space-time over which their parameters are distributed. Conspansive domains interpenetrate against the background of past events at the inner expansion rate c, defined as the maximum ratio of distance to duration by the current scaling, and recollapse through quantum interaction. Conspansion thus defines a kind of absolute time metering and safeguarding causality. Interpenetration of conspansive domains, which involves a special logical operation called unisection, distributed intersection, combining aspects of the set theoretic operations union and intersection, creates an infocognitive relation of sufficiently high order to effect quantum collapse. Output is selectively determined by especially interference and reinforcement within and among metrical layers. Because self-configurative spacetime grammar is conspansive by necessity, the universe is necessarily subject to a requantizative accelerative force that causes its apparent expansion. The force in question, which Einstein symbolized by the cosmological constant lambda, is all but inexplicable in any non-conspansive model. That no such model can cogently explain it is why he later relented and described lambda as the greatest blunder of his career. By contrast, the CTMU requires it as a necessary mechanism of SCSPL grammar. Thus, Recent experimental evidence, in particular, recently acquired data on high redshift type Ia supernovae that seem to imply the existence of such a force, may be regarded as powerful, if still tentative, empirical confirmation of the CTMU. Metrical layering. In a conspansive universe, the spacetime metric undergoes constant rescaling. Whereas Einstein required a generalization of Cartesian space embodying higher-order geometric properties like spacetime curvature, conspansion requires a yet higher order of generalization in which even relativistic properties, for example spacetime curvature inhering in the gravitational field, can be progressively rescaled. Where physical fields of force control or program dynamical geometry, and programming is logically stratified as in Nest, fields become layered stacks of parallel distributive programming that decompose into field strata, conspansive layers, related by an intrinsic requantization function inhering in, and logically inherited from, the most primitive and connective layer of the stack. This storage process by which infocognitive spacetime records its logical history is called metrical layering. Note that since storage is affected by inner expansive domains which are internally atemporal, this is to some extent a misnomer reflecting weaknesses in standard models of computation. The metrical layering concept does not involve complicated reasoning. It suffices to note that distributed, as in event images, are outwardly distributed in layers of parallel computation by inner expansion, effectively means of zero intrinsic diameter with respect to the distributed attribute. If an attribute corresponding to a logical relation of any order is distributed over a mathematical or physical domain, then interior points of the domain are undifferentiated with respect to it, and it need not be transmitted among them. Where space and time exist only with respect to logical distinctions among attributes, metrical differentiation can occur within inner expansive domains, IEDs, only upon the introduction of consequent attributes relative to which position is redefined in an overlying metrical layer, and what we usually call the metric is a function of the total relationship among all layers. The spacetime metric thus amounts to a Venn diagrammatic conspansive history in which every conspansive domain, light cone cross-section, Venn sphere, has virtual zero diameter with respect to distributed attributes, despite apparent non-zero diameter with respect to metrical relations among subsequent events. What appears to be non-local transmission of information can thus seem to occur. Nevertheless, the CTMU is a localistic theory in every sense of the word. Information is never exchanged faster than conspansion, i.e. faster than light. The CTMU's unique explanation of quantum non-locality within a localistic model is what entitles it to call itself a consistent extension of relativity theory, to which the locality principle is fundamental. Metrical layering lets Neo-Cartesian spacetime interface with predicate logic in such a way that in addition to the set of localistic spacetime intervals riding atop the stack, and subject to relativistic variation in space and time measurements, there exists an underlying predicate logic of spatiotemporal contents obeying a different kind of metric. Spacetime thus becomes a logical construct reflecting the logical evolution of that which it models, thereby extending the Lorentz-Minkowski-Einstein generalization of Cartesian space. Graphically, the CTMU places a logical, stratified computational construction on spacetime, implants a conspansive requantization function in its deepest, most distributive layer of logic, or highest, most parallel level of computation, and rotates the spacetime diagram depicting the dynamical history of the universe by 90 degrees along the space axis. Thus, one perceives the model's evolution as a conspansive overlay of physically parametrized Venn diagrams directly through the time, SCSPL grammar, axis rather than through an extraneous z-axis artificially separating theorist from diagram. The cognition of the modeler, his or her perceptual internalization of the model, is thereby identified with cosmic time, and infocognitive closure occurs as the model absorbs the modeler in the act of absorbing the model. To make things even simpler, the CTMU equates reality to logic, logic to mind, and, by transitivity of equality, reality to mind. Then it makes a big Venn diagram out of all three, assigns appropriate logical and mathematical functions to the diagram, and deduces implications in light of empirical data. A little reflection reveals that it would be hard to imagine a simpler or more logical theory of reality. The CTMU and quantum theory. The microscopic implications of conspansion are in remarkable accord with basic physical criteria. In a self-distributed, perfectly self-similar universe, every event should mirror the event that creates the universe itself. In terms of an implosive inversion of the standard Big Bang model, this means that every event should to some extent mirror the primal event, consisting of a condensation of Higgs energy distributing elementary particles and their quantum attributes, including mass and relative velocity, throughout the universe. To borrow from evolutionary biology, space-time ontogeny recapitulates cosmic phylogeny. Every part of the universe should repeat the formative process of the universe itself. Thus, just as the initial collapse of the quantum wave function, QWF, of the causally self-contained universe is internal to the universe, the requantitative occurrence of each subsequent event is topologically internal to that event, and the cause spatially contains the effect. The implications regarding quantum non-locality are clear. No longer must information propagate at superluminal velocity between spin-correlated particles, instead, the information required for example, spin conservation is distributed over their joint ancestral, i.e. the virtual zero-diameter spatiotemporal image of the event that spawned both particles as a correlated ensemble. The internal parallelism of this domain, the fact that neither distance nor duration can bind within it, short-circuits spatiotemporal transmission on a logical level. A kind of logical superconductor, the domain offers no resistance across the gap between correlated particles. In fact, the gap does not exist. Computations on the domain's distributive logical relations are as perfectly self-distributed as the relations themselves. Equivalently, any valid logical description of space-time has a property called hology, whereby the logical structure of the nest universal automaton, that is, logic in its entirety, distributes over space-time at all scales along with the automaton itself. Notice the etymological resemblance of hology to holography, a term used by physicist David Bohm to describe his own primitive non-local interpretation of QM. The difference, while Bohm's pilot wave theory was unclear on the exact nature of the implicate order forced by quantum non-locality on the universe, an implicate order inevitably associated with conspansion, the CTMU answers this question in a way that satisfies Bell's theorem with no messy dichotomy between classical and quantum reality. Indeed, the CTMU is a true localistic theory in which nothing outruns the conspansive mechanism of light propagation. The implications of conspansion for quantum physics as a whole, including wave function collapse and entanglement, are similarly obvious. No less gratifying is the fact that the non-deterministic computations posited in abstract computer science are largely indistinguishable from what occurs in QWF collapse, where just one possibility out of many is inexplicably realized, while the CTMU offers an explanation called the extended superposition principle, or especially, standard physics contains no comparable principle. In conspansive space-time, time itself becomes a process of wave-particle dualization mirroring the expansive and collapsative stages of SCSPL grammar, embodying the recursive syntactic relationship of space, time, and object. There is no alternative to conspansion as an explanation of quantum non-locality. Any non-conspansive, classically oriented explanation would require that one of the following three principles be broken: the principle of realism, which holds that patterns among phenomena exist independently of particular observations, the principle of induction, whereby such patterns are imputed to orderly causes, and the principle of locality, which says that nothing travels faster than light. The CTMU, on the other hand, preserves these principles by distributing generalized observation over reality in the form of generalized cognition, making classical causation a stable function of distributed SCSPL grammar, and ensuring by its structure that no law of physics requires faster-than-light communication. So if basic tenets of science are to be upheld, Bell's theorem must be taken to imply the CTMU. As previously described, if the conspondating universe were projected in an internal plane, its evolution would look like ripples, infocognitive events, spreading outward on the surface of a pond, with new ripples starting in the intersects of their immediate ancestors. Just as in the pond, old ripples continue to spread outward in ever deeper layers, carrying their virtual zero diameters along with them. This is why we can collapse the past history of a cosmic particle by observing it in the present, and why, as surely as Newcomb's demon, we can determine the past through regressive metric layers corresponding to a rising sequence of nest strata leading to the stratum corresponding to the particle's last determinant event. The deeper and farther back in time we regress, the higher and more comprehensive the level of nest that we reach, until finally, like John Wheeler himself, we achieve observer participation in the highest, most parallelized level of nest, the level corresponding to the very birth of reality. Appendix A. Analysis is based on the concept of the derivative, an instantaneous rate of change. Because an instant is durationless, of zero extent, while a change is not, this is an oxymoron. Cauchy and Weierstrass tried to resolve this paradox with the concept of limits, they failed. This led to the discovery of non-standard analysis by Abraham Robinson. The CTMU incorporates a conspansive extension of non-standard analysis in which infinitesimal elements of the hyperreal numbers of NSA are interpreted as having internal structure, i.e. as having non-zero internal extent. Because they are defined as being indistinguishable from zero in the real numbers Rn, i.e. the real subset of the hyperreals Hn, this permits us to speak of an instantaneous rate of change. While the instant in question is of zero external extent in Rn, it is of non-zero internal extent in Hn. Thus, in taking the derivative of, for example, x2, both sides of the equation dy/dx equal to x plus dx, where d equal delta equal a generic increment, are non-zero, simultaneous and in balance. That is, we can take dx to 0 in Rn and drop it on the right with no loss of precision while avoiding a division by 0 on the left. More generally, the generic equation lim_z registered 0 ird/dx equal lim_z registered 0 irf, x plus dx, f, x/dx. No longer involves a forbidden division by 0, the division takes place in h, while the zeroing out of dx takes place in r, h and r, respectively inside and outside the limit and thus associated with the limit and the approach thereto, our model theoretically identified with the two phases of the conspansion process L-sim and L-out, as conventionally related by wave-particle duality. This leads to the CTMU sum over futures, SOF, interpretation of quantum mechanics, incorporating an extended superposition principle, especially, under the guidance of the CTMU Telek principle, which asserts that the universe is intrinsically self-configuring. In this new CTMU extension of non-standard analysis, the universe can have an undefined, virtually zero, external extent while internally being a conspansively differentiable manifold. This, of course, describes a true intrinsic geometry incorporating intrinsic time as well as intrinsic space, so much for relativity theory. In providing a unified foundation for mathematics, the CTMU incorporates complementary extensions of logic, set theory, and algebra. Because physics is a blend of perception, observation and experiment, and mathematics, providing mathematics with a unified foundation, by interpreting it in a unified physical reality, also provides physics with a unified foundation, by interpreting it in a unified mathematical reality. Thus, by conspansive duality, math and physics are recursively united in a dual-aspect reality wherein they fill mutually foundational roles. If you want to know more about how the CTMU is derived using logic and set theory, check out these online papers. On Absolute Truth. Introduction to the CTMU. CTMU, a new kind of reality theory, PDF. I'm currently working on additional papers. Appendix B. Because the value of R can only be theoretically approximated, using R or even R1 to describe requantization makes it appear that we are simply using one theory to justify another. But the R to R1 inversion comes with an addition of logical structure, and it is this additional structure that enables us to define a high-level physical process, conspansion, that opposes gravity and explains accelerating redshift. Conspansive requantization is uniform at all scales and can be seen as a function of the entire universe or of individual quanta. Every part of the universe is grammatically substituted, or injectively mapped, into an image of its former self, an image endowed with computational functionability. To understand this, we must take a look at standard cosmology. Standard cosmology views cosmic expansion in terms of a model called ERSU, the expanding rubber sheet universe. For present purposes, it is sufficient to consider a simplified two-spheric ERSU whose objects and observers are confined to its expanding two-dimensional surface. In ERSU, the sizes of material objects remain constant while space expands like an inflating balloon. If objects grew at the rate of space itself, expansion could not be detected. At the same time, spatial distances among co-moving objects free of peculiar motions remain fixed with respect to any global co-moving coordinate system. In this sense, the mutual rescaling of matter and space is symmetric. But either way, the space occupied by an object is considered to stretch without the object itself being stretched. Aside from being paradoxical on its face, this violates the basic premise of the pure geometrodynamic view of physical reality, which ultimately implies that matter is space in motion relative to itself. If we nevertheless adhere to ERSU and the Standard Model, the expansion rate, prior to gravitational opposition, is constant when expressed in terms of material dimensions, i.e., with respect to the original scale of the universe relative to which objects remain constant in size. For example, if ERSU expansion were to be viewed as an outward layering process in which the top layer is now, the factor of linear expansion relating successive layers would be the quotient of their circumferences. Because object size is static, so is the cosmic time scale when expressed in terms of basic physical processes. At any stage of cosmic evolution, time is scaled exactly as it was in the beginning. The idea behind the CTMU is to use advanced logic, algebra, and computation theory to give space-time a stratified computational or cognitive structure that lets ERSU be inverted and ERSU paradoxes resolved. To glimpse how this is done, just look at the ERSU balloon from the inside instead of the outside. Now imagine that its size remains constant as thin, transparent layers of parallel distributed computation grow inward, and that as objects are carried towards the center by each newly created layer, they are proportionately resized. Instead of the universe expanding relative to objects whose sizes remain constant, the size of the universe remains constant and objects do the shrinking along with any time scale expressed in terms of basic physical processes defined on those objects. Now imagine that as objects and time scales remain in their shrunken state, layers become infinitesimally thin and recede outward, with newer levels of space becoming denser relative to older ones and older levels becoming stretched relative to newer ones. In the older layers, light which propagates in the form of a distributed parallel computation retroactively slows down as it is forced to travel through more densely quantized overlying layers. To let ourselves keep easy track of the distinction, we will give the ERSU and inverted ERSU models opposite spellings. i.e., inverted ERSU will become USRE. This turns out to be meaningful as well as convenient, for there happens to be an apt descriptive phrase for which USRE is acronymic, the universe as a self-representational entity. This phrase is consistent with the idea that the universe is a self-creative, internally iterated computational endomorphism. It is important to be clear on the relationship between space and time in USRE. The laws of physics are generally expressed as differential equations describing physical processes in terms of other physical processes incorporating material dimensions. When time appears in such an equation, its units are understood to correspond to basic physical processes defined on the sizes of physical objects. Thus, any rescaling of objects must be accompanied by an appropriate rescaling of time if the laws of physics are to be preserved. Where the material contents of space-time behave in perfect accord with the medium they occupy, they contract as space-time is requantized, and in order for the laws of physics to remain constant, time must contract apace. For example, if at any point it takes n time units for light to cross the diameter of a proton, it must take the same number of units at any later juncture. If the proton contracts in the interval, the time scale must contract accordingly, and the speed and wavelength of newly emitted light must diminish relative to former values to maintain the proper distribution of frequencies. But meanwhile, light already in transit slows down due to the distributed stretching of its deeper layer of space, i.e., the superimposition of more densely quantized layers. Since its wavelength is fixed with respect to its own co-moving scale, and that of the universe as a whole, wavelength rises and frequency falls relative to newer, denser scales. Complementary recalibration of space and time scales accounts for cosmic redshift in the USRE model. But on a deeper level, the explanation lies in the nature of space and time themselves. In ERSU, time acts externally on space, stretching and deforming it against an unspecified background and transferring its content from point to point by virtual osmosis. But in USRE, time and motion are implemented wholly within the spatial locales to which they apply. Thus, if cosmic redshift data indicate that expansion accelerates in ERSU, the inverse USRE formulation says that space-time requantization accelerates with respect to the iteration of a constant fractional multiplier, and that meanwhile, inner expansion undergoes a complementary deceleration relative to the invariant size of the universe. In this way, the two phases of conspansion work together to preserve the laws of nature. The crux, as ERSU expands and the cosmological scaling factor R rises, the USRE inverse scaling factor 1/R falls. This factor is expressed elsewhere in a time-independent form R. As ERSU swells and light waves get longer and lower in frequency, USRE quanta shrink with like results. In either model, the speed of light falls with respect to any global comoving coordinate system, Cn/C0 equal R0/Rn equal Rn1/R01. The idea that C is an absolute constant in ERSU is oversimplistic. Like material dimensions, the speed of light can be seen to change with respect to comoving space in cosmological time. But only in USRE does the whole process become a distributed logico-mathematical endomorphism effected in situ by the universe itself, a true local implementation of physical law rather than a merely localistic transfer of content based on a disjunction of space and logic. The point is to preserve valid ERSU relationships while changing their interpretations so as to resolve paradoxes of ERSU cosmology and physics. In Noesis/ES 139, it was remarked that if the universe were projected on an internal plane, space-time evolution would resemble spreading ripples on the surface of a pond, with new ripples starting in the intersects of old ones. Ripples represent events, or nomological, SCSPL syntactic, combinations of material objects implicit as ensembles of distributed properties, quantum numbers. Now we see that outer, subsurface, ripples become internally dilated as distances shorten and time accelerates within new ripples generated on the surface. CTMU monism says that the universe consists of one dual-aspect substance, infocognition, created by internal feedback within an even more basic, one-aspect, substance called telesis. That everything in the universe can manifest itself as either information or cognition, and on combined scales, as both, can easily be confirmed by the human experience of personal consciousness, in which the self exists as information to its own cognition, i.e., as an object or relation subject to its own temporal processing. If certain irrelevant constraints distinguishing a human brain from other kinds of object are dropped, information and cognition become identical to spatial relations and time. In a composite object, like a brain, consisting of multiple parts, the dual aspects of infocognition become crowded together in space-time. But in the quantum realm, this monic duality takes the form of an alternation basic to the evolution of space-time itself. This alternation usually goes by the name of wave-particle duality, and refers to the inner expansive and collapsative phases of the quantum wave function. Where ripples represent the expansive, or cognitive, phase, and their collapsation into new events determines the informational phase, the above reasoning can be expressed as follows: as the infocognitive universe evolves, the absolute rate of spatiotemporal cognition Cn at time n, as measured in absolute, conserved, units of space-time, is inversely proportional to the absolute information density Rn/R0 of typical physical systems, i.e., to the concentration of locally processed physical information. As light slows down, more SCSPL grammatical, generalized cognitive, steps are performed per unit of absolute distance traversed. So with respect to meaningful content, the universe remains steady in the process of self-creation.